One reason that I seek a higher intelligence in outer space is because I don't find it very often here on Earth. Science offers us a way of converging to the truth, which is looking for data and evidence about what nature really is. It's not a matter of opinion. My point is they would grow to become better than us. And I have no problem if we would be remembered by the AI astronauts that we sent to interstellar space rather than by what we managed to accomplish on this rock.
Harvard Professor Avi Loeb, director of the Institute for Theory and Computation at the Center for Astrophysics since 2007, ex-chair of the Harvard Astronomy Department and founder of the Black Hole Initiative, joins the 632 nanometer team for an epic discussion about science, philosophy, humans, life, hunting for alien artifacts, AI, and the universe. They discuss the details of Avi's mainstream astronomy work, his path from a farm in Israel to tenure at Harvard, and, of course, his brilliant, inspiring, and controversial search for rigorous evidence of intelligent aliens.
Where was your PhD? What was the topic? And what is the thesis?
Well, let me start since Lex Friedman may be listening. Science is better than politics. And I will elaborate on that. But the one good thing about science is it allows you to maintain your childhood curiosity because you don't need to know the answer in advance. And in politics, it's all about being the adult in the room and telling others what your belief is without necessarily having evidence for it. And as long as you have a crowd that follows you, you're successful in politics. But in science, it's not about the crowd. It's not about social media. It's not about being popular or trying to get as much power as possible. It's about listening to nature. And it's a learning experience. And that's a great privilege because, you know, we pass through life pretending to be something that we aren't. And nature is humbling. Albert Einstein, between 1935 and 1940, made the three mistakes, very fundamental mistakes. He argued that black holes do not exist because he said, well, how do you make a black hole from the collapse of a star? And stars are often spinning, so the spin of stars will prevent black holes from forming. He also argued that gravitational waves do not exist. He wrote a paper about it with his postdoc, Nathan Rosen, saying, well, gravitational waves can be just mathematical artifacts of my theory. And then he argued that quantum mechanics should not have spooky action at a distance. Again, with Nathan Rosen and another postdoc, Podolsky. And all three were proven to be wrong by experimental teams that got the Nobel Prize over the past decade. So the past decade included 3 Nobel Prizes for the discovery of black holes, for the discovery of gravitational waves, and for quantum entanglement, which shows you that nature can show Einstein wrong. Even the most accomplished scientist at the end of his career, when he had all the experience, made mistakes. Now, he was not a good politician because as a politician, you would not take risks. You would basically create an echo chamber that amplifies your ego and say, you know, this is what I discovered, special relativity, general relativity, and that would be the political thing to do. But he was curious about nature and made mistakes. So my point is, science allows us to stay kids, curious, wondering about the world. I haven't changed much since I was a child, and I see that as a great privilege. And I refuse to surrender to external pressure to say what other people want me to say, because otherwise, why would I do science? The whole idea of tenure in academia is to give you job security so you can speak freely. As a politician, you never have job security. So I'm saying science is better than politics. And by the way, I said that at the Munich Security Conference a year ago. They invited me as the first scientist to speak in that forum. And I was surrounded by heads of state, you know, including Volodymyr Zelensky. And I noticed that on the roof of that hotel, there were snipers with black head covers. They were not there to protect me. And so it showed me that being a politician is also very risky. People want to kill you. Nobody wants to kill me. So here is another privilege of being a scientist. You can do what you like without people being angry at that, in principle. Except for other scientists that are sometimes jealous, of what you're doing. So anyway, that's why I'm happy to do what I'm doing, and I haven't changed much since I was a kid. And we can talk more about the details.
Mm-hmm. So when was the turning point that you realized that, say, you would like to be a scientist? I mean, was it like in early childhood, or did it happen later?
Never. As a kid, I was interested in the big questions. And the big questions are in the realm of philosophy, about our existence. And I read a lot of philosophy books. I was mainly impressed by existentialism, French philosophers like Jean-Paul Sartre, Albert Camus. And the reason I like them is because they don't pretend to know something that is different from, their humble existence. I particularly, I was very disappointed, sitting at the dinner table as a kid and asking a difficult question, and then the adults in the room would give you an answer that didn't make sense. And I thought, I want to figure it out. And as a kid, I grew up on a farm, and I used to go to the hills of the village.
Which part of Israel? Where was your farm?
Oh, it's near Tel Aviv. It's about 15 miles or so from there. And so I used to drive a tractor on the weekends and just read philosophy books there. And I thought of becoming a philosopher, but I was born in the Middle East,
Wow.
which means that, especially in Israel, there is obligatory military service. And so the closest thing that I could do to thinking broadly about, my existence is physics, science, because there was a program within the military that allowed the members, they were selected, there were 20 out of thousands of the yearly applicants that were selected. And the program allowed those who are selected to work on research in science and technology that is beneficial for the defense of the country. And so I made a compromise. I said, well, physics is not really my true love, but I'm willing to compromise and do that because it's the closest thing that I can do to philosophy. And I was good at it. And so I went there, and I was also good in sports. So it made it easier for me because we had training through all the military sections. So we parachuted, we drove tanks. So just for us to get a sense of what it's like to be a soldier. But then I developed an idea that ended up being selected for the first international project by the so-called Strategic Defense Initiative, Star Wars, of President Ronald Reagan. We had a visit by General Abramson. He's still alive. I think he's in his 80s right now. But he came to visit Israel and selected our project after I gave him a presentation that was funded. And that project brought me to Washington, D.C. quite often.
So the title of the thesis was Particle Acceleration to High Energies and Amplification of Coherent Radiation by Electromagnetic Interactions in Plasma. So this is like the space lasers, basically.
No, actually, the project was more about using electric energy to propel masses to high velocities, because the conventional...
Like electromagnetic?
Yes, stored electromagnetic. The conventional way of firing, rockets or bullets or whatever is to use chemical propellants. And they are limited by the speed of sound of the material, because once the projectile moves faster than the speed of sound, the gas that is pushing it cannot catch up with it. And so because propellants are made of specific heavy elements, you can't really reach very high, even at high temperatures, you can't reach very high speed of sound. And on the other hand, if you inject the energy from an external source, like capacitors that store electric energy, then in principle you can deposit it in material that has a very low molecular weight so that you get a very high sound speed. So that was actually a patent and a project that we followed.
This is still for like a rocket engine. It's not like a rail gun where you have a piece of metal and you're accelerating it with magnets.
Right. It's alternative
It's like an
to railgun.
ion. It's like an ion rail gun or something.
Well, you're using gas to push.
It's still gas. It's still gas. I see.
You're providing the heat from electric storage.
Interesting.
And so that ended up being a project that was funded a few $1 million a year and brought me to Washington quite frequently. And in one of the visits, it was suggested to me by the Pope of plasma physics. I mean, whenever you create hot gas, that's considered plasma. And the Pope at the time was Marshall Rosenbluth. He was the most accomplished plasma physicist in the US, and he liked what I'm doing. And I asked him, where should I visit, when I finish my PhD and think about the postdoctoral fellowship? And he said the Institute for Advanced Study at Princeton would be a good place because he was a professor there before a decade earlier. So I contacted the administrator there and said, I would like to visit for a weekend on one of my trips. And she said, who are you? Please send me your CV. I will share it with faculty, and I will let you know if we welcome your visit. So I sent it to her. I had 11 publications at the time. It was just before I completed my PhD. And she said, okay, you can come and visit. I arrived at her office and she said, well, we have only one faculty member who has time, and that is Freeman Dyson. And I knew him from textbooks. And I said, wow, that would be amazing to meet him. So she brought me to Freeman Dyson, and he said, oh, you are from Israel. Actually, we have a faculty member who likes Israelis. His name is John Bakal. He's married to one. And maybe he's around. So he called him, and John was around, and we went to lunch. And John invited me for a month. And at the end of the visit, he said, we would like to offer you a 5-year fellowship, postdoctoral fellowship, which was an offer that I could not decline, just like in The Godfather. And I went down the stairs at the time, and I saw one of the 5-year members, and I said to him, John just offered me a position. And he said, how is that possible? We are supposed to discuss you this afternoon. And then they had a discussion. And so they said, John asked them, what do you think about Avi? And they said, well, you already offered him, didn't you? And he said, yeah, I offered him, but I just want to hear your opinions. That was his approach to making decisions. And he gambled on me. I am currently the director of the Institute for Theory and Computation at Harvard. I was chair of the astronomy department at Harvard for 9 years, the longest serving chair, 3 terms. And I was the founding director of the Black Hole Initiative at Harvard. I had a lot of postdoctoral fellows that I appointed, more than 100, or actually maybe a few hundred. And I cannot imagine a situation where I would make a decision without a committee, because nowadays, it's a different world. It's not the same as it was back then. But anyway, the previous world allowed me to start a career in astrophysics. So one condition that he put was, as long as you switch to astrophysics, and I didn't know how the sun shines. That was his main focus at the time, how the sun shines, because he was studying neutrinos emitted by nuclear reactions. The sun is just a nuclear reactor that nature produced. And we should see the decay products. I mean, when you have nuclear reactions, you produce neutrinos. And he calculated how many, and the experiment found less. So that was his main focus. I didn't know how the sun shines. I had to learn that. I had to learn, what galaxies are, clusters. So I didn't know any of the vocabulary. It was a very difficult time for me to come for 5 years, surrounded by brilliant people that are very competitive. But I had to, just like there is this folk tale about the Baron Munchausen that once got into mud and had to pull himself out of the mud, which is impossible, based on what we know in physics. He didn't have any rocket to lift him. But I felt like that because I didn't have any training in astrophysics. I had to sort of manage to lift myself up. And then there was a position at Harvard, and nobody wanted it because the chance of getting promoted to tenure were quite minuscule. And so
why were they low?
Because they were very arrogant at the time. They thought that they can offer it to anyone that would come, and therefore they can recruit junior faculty without keeping them. So they were just used for. In principle, they can teach, they can mentor, but then at the end, when they have to decide whether to keep a junior faculty and promote the junior faculty to tenure, they will consider the best people in the world in the same area, and they are not committed. It's not a marriage. They're not committed. So many junior faculty were not promoted around that time.
And what was the survival rate for the junior faculty?
At the time, it was of the order of, I would say, 10%.
Wow. So 1 in 10.
Yeah, so the previous person who was tenured was 15 years earlier. And so they offered it to someone who said, thank you very much. I prefer to take a faculty job in the Netherlands because there it's a real job, whereas at Harvard, it's just temporary. So they offered it to me as a second choice. And I accepted it because I always had job security. I could always go back to the farm. I wanted to do philosophy anyway, And so I didn't feel as if it's a threat. And then 3 years down the line, I finished my PhD at age 24. So I was relatively young at the time. And 3 years after getting to Harvard, Cornell had an open tenured position, and they chose me. I didn't know anyone there. I went there, gave a talk, and they decided to offer it to me.
What were you working on at Harvard? During that
time. The subject that I invented for myself that not many people worked on or were interested in is the scientific version of the story of Genesis, which is how was the first light produced. And I'm not talking about the light from the Big Bang, from the hot, dense phase of the early universe, but the light that was produced afterwards by stars. And the question is, how did the first stars form? The first galaxies, and when, and what was the imprint that those stars left on the surroundings? Because these are our cosmic roots. We exist. We exist because of life that is chemistry in liquid water. Liquid water, has oxygen in it. A water molecule has oxygen. Oxygen was not produced in the Big Bang. At any meaningful abundance. So it was produced in the interiors of stars that cooked hydrogen, helium, and so forth, and made oxygen. And so our story as biological beings starts when the first stars formed. It actually starts in the Big Bang, and we can talk more about it. But so I wanted to understand that. It's it appears in the first chapter of Genesis, Genesis in the Old Testament. And I wanted to check if that storyline is correct. So that's what I focused on. And
it's basically saying, is there at least a model that explains the formation of stars from before they existed?
Well, not only a model that explains the formation,
or like evidence from
making
observations,
detailed predictions about when it had happened in the standard model of cosmology, and how can we observe those stars? What would be the signatures of them? And in fact, I was a couple of years after arriving at Harvard, I was selected to the advisory board that designed the Webb telescope. Back then, it was called the Next Generation Space Telescope, because one of the main goals of the Webb telescope that we now have was to operate in the infrared and search for the light from the first stars and galaxies. And the reason you need to work in the infrared is because optical light, optical light like the sun is emitting would be, the wavelength of those photons will be stretched by the cosmic expansion to the infrared.
How close is it to the microwave background radiation? Like what's the temperature of like the first star?
No, so the microwave background today is 2.73 degrees Kelvin above absolute zero. Back then, when the first stars formed, it was an order of magnitude larger.
Okay.
But the surface temperature of the first stars was of the order of 100,000 degrees Kelvin. These were more massive than nearby stars.
Only 100,000?
100,000.
Because now it's like...
No, now
the surface is
sun?
10,000.
Yeah, we're talking about the surface. Of course. And inside the first stars, it was even higher than that, than the sun. The sun is a temperature of about 10 million degrees or so in the core, okay?
Yeah,
Or
the fusion happening.
Yeah, 13.5 to be, million degrees Kelvin. But the surface of the sun is basically giving us the luminosity that we see. And it's at about a temperature close to 5,000 degrees. And it emits a black body radiator like the sun emits in the optical band. And that's why our eyes are sensitive to that band, because it allowed us to survive in nature. So if we were living next to a black hole, let's say, that emits X-rays, we might have had X-ray eyes.
That would be a much difficult task because the material properties in X-rays, it's
I know.
almost identical. And
But natural selection, Darwinian evolution, would have favored animals that have sensors to X-rays if we were next to a black hole that emits X-rays. Or, massive stars emit ultraviolet radiation, so we would be able
to see.
Now, of course, we can see only the radiation that is filtered by the atmosphere. Some parts of it are absorbed, like as we know, ultraviolet is pretty much blocked by ozone and other constituents. But at any event, if you think about life on Earth, it's very much shaped by the sun. And the early stars were very different. They were much hotter and much more massive.
What's the reason for that? Just availability of matter, like the clouds were denser to begin with, so they make denser stars, or what's the...
No, it's the fact that the Big Bang did not produce heavy elements. It produced primarily hydrogen and helium.
Yep.
Hydrogen is just a proton and an electron. These were available from the start. Before the universe was very hot, at very early times, even the protons were broken into their constituent quarks. But, once the temperature of the universe dropped below 10 billion degrees, protons and neutrons formed. And then hydrogen became the most prominent, most abundant element. By the way, speaking about that, there is a fascinating story because we are born on a rock, right? The Earth. And so what we see around us is not representative of the universe. All these heavy elements, iron, silicon, they were produced in the interiors of stars. And actually, just 100 years ago, it was believed by astronomers that the composition of the sun is the same as the Earth. Okay? What else? The Earth is sort of residue left from the formation of the sun. And then the first PhD in astronomy at Harvard University, well, it was not Harvard. She was at Radcliffe at the time, but and in fact, there was no astronomy department at Harvard at the time. So her thesis was actually the trigger for creating the astronomy department at Harvard, and she became one of the department chairs later on, and she lived not far from where I live. Her name is Cecilia Payne-Kopashkin, and she realized, based on analyzing the data on the spectrum, the breakdown of intensity as a function of wavelength coming from the sun, that in fact, and it was around the time when quantum mechanics was discovered, that people understood that how to relate spectral lines to specific atoms. So you can look for the fingerprints of different types of atoms at the surface of the sun, and she concluded that hydrogen is the most abundant element. And that was a shock. And she put it in her thesis, but then on her thesis committee were several very influential astronomers. For example, Henry Norris Russell, who was the director of the Princeton University Observatory. And he dissuaded her. He said, to take it out of her thesis, he said, we all know that the sun has the same composition as the Earth. And she took it out because, she was just a student, and at the time also women were not treated fairly. And then, just to prove her wrong, he dedicated the next 5 years to checking what she was arguing and found out, published in a paper, that she was right. And it's not only that hydrogen makes the sun the most abundant element in the sun, it's actually the most abundant element in the universe. And just think about it. We know it only for 100 years. Quantum mechanics was discovered just 100 years ago. We are really at our infancy in terms of modern science and technology. I lived through half of modern science. My life is spanning half of modern science, which is
if you
amazing.
pick up a book called Modern Physics, it's like the last 100 years, basically.
Yeah. And so, by the way, it raises an interesting question, because when you select a random day in your life, it's very unlikely to be the first day or the last day, right, of your life.
So why are we living through this moment?
No,
that is very strange. I see what you're saying.
If you take that to its conclusion, it means that we may have another 100 years and that's it, or maybe a few centuries at most. But given the acceleration of artificial intelligence, it's an exponential process, with a characteristic time scale of a few years, and so it's quite possible that we have even less than a century left, which raises a lot of interesting issues. But the good thing about the human spirit, as far as I can tell, is that, we can go against all odds, that we can decide to survive. And it would be very different from the way Darwin thought about it, because Darwin, it's all kind of the fittest survives, and it's sort of a game where you have various options being explored and so forth. But with humans, I think there is a sense that you can actually plan in principle. I mean, if you read the newspapers, you don't get that impression. There is a lot of chaos in human history. But on the other hand, we have that opportunity to plan ahead and to survive. And that, by the way, just if I had to summarize it with one sentence, we should not focus on this rock that we were born on. There is much more real estate out there. And we keep, we invest $2.4 trillion in military budgets worldwide just to kill other people or protect ourselves from others killing us. That's not a very intelligent thing to do. And one reason that I seek a higher intelligence in outer space is because I don't find it very often here on Earth.
By the way, speaking of Earth, so you said an interesting thing, that the Earth is like a rock which was before like a part of the sun. Would it be like a good allegory that Earth is like a rib coming from the sun, if we come back to the Genesis?
Well, okay, so we have to discuss how the sun was made. It started from a cloud, a local cloud of gas.
But just one point, you have to eventually come back and explain why the initial stars were bigger.
Okay,
we lost that. Yes.
Okay, let me first answer this.
Sounds good.
There was a cloud of gas that was enriched with heavy elements by exploding stars. Stars that were massive, burned hydrogen and helium into heavy elements, and then exploded. So they spread the heavy elements, and
that was the fusion process.
The fusion made heavy elements by combining, and it ended with iron, because nuclear physics tells you that it's the most stable nucleus. Okay, so by fusing, you can't gain energy you can't build heavier elements and gain energy. So fusion ends with iron. That's it. And in fact, massive stars.
Or it favors iron. So you get lower and lower abundance as you go. So you get some uranium, but not much.
No, you don't get.
Where does the uranium come from?
From fusion. You get it from other processes. For example, when a massive star eventually develops a core, an iron core, which actually it has a structure that includes onion shells of other elements based on when they were burned. And then eventually it explodes in a supernova. So it ejects the envelope that contains all these other heavy elements. But the core of the massive star, if it's not too massive, if it's somewhere between 8 and 25 solar masses, the core ends up in a neutron star, which is just like a giant nucleus with somewhere between 1 and 2.5 solar masses. And this nucleus is made only of neutrons. Now, if you make 2 of these and they are in a pair, they could eventually spiral towards each other by emitting gravitational waves, and they will collide. So the collision of 2 neutron stars, for example, would create neutron-rich material that will be spewed out from the collision. You would get some ejecta. Maybe a few % of the mass of the collision will end up outside of the merger remnant, and you would have nuclei that are rich in neutrons, and these are not stable. So what happens to this material that is neutron-rich is that it decays radioactively and makes the heavier elements than iron, makes uranium, gold. So the sources of all evil on Earth, gold and uranium, are merging neutron stars, you see? And if you happen to be on a planet close to such an event, you would get a lot of uranium and gold. And so, we should be careful of civilizations that were born close to such a collision, because, they might have a lot of atomic weapons, but they would also have a lot of gold, okay? But by the way, if you have a lot of gold, you're not necessarily rich, because it becomes so abundant that nobody pays.
So should we go to Mercury to get more gold, since it's the closest to the sun?
No. So what I said is the solar system was enriched, but it was not very close to a neutron merger event. So it's sort of enriched at the average abundance of heavy elements within the Milky Way galaxy. So when you have these neutron star mergers, they enrich mostly their immediate environment, but eventually the material gets mixed, and we are sort of at the average. Okay. By the way, it's a very
that in itself is actually interesting, because we're not at an extreme point. So that seems like life is not, at least not dependent on being at an extreme of.
Right. We are also not at the center of the galaxy, right? Which is a very hostile environment, because there are lots of stars buzzing by. There is a supermassive black hole there. There are things to be said about where we are located. The real estate that we have is fortunate. We exist on it.
It's the Mediterranean of the galaxy, something like this.
But it's important to keep in mind that there are 100 billion Earth-Sun systems probably in the Milky Way. If you take the latest statistics about how likely it is to, based on all the data we have on exoplanets, how likely it is to have an Earth mass planet at the right distance from a star to have liquid water on the surface and the chemistry of life, it's one house that we live in out of 100 billion that we see in our cosmic street. And this is only within the Milky Way galaxy. So now, when my daughters were infants, I have 2 daughters, when they were babies, they were in the crib, okay? And it's just like AI systems. The quality of your thoughts depend on your training set, okay? So as babies, the training data set was limited to the environment of the crib, okay? But then they started crawling and walking at home, and their data set increased to include the entire house that we are speaking in. And they could look through the windows. Okay, so they saw other houses. Now, what my colleagues are doing, the astrobiologists, they're saying, oh, look at all these other houses. Yeah, we are aware of the fact that there could be many houses similar to ours, but it would be an extraordinary claim that requires extraordinary evidence to believe that there are infants like us in those houses. We deserve much more attention because we might be unique and special. And this is not just the astrophysics mainstream. It's also people like Elon Musk saying, oh, we should go to Mars because we might be alone. And, Peter Thiel, after the last election, appeared in several podcasts. And in one of them, he said, you should never bet against Elon. And so the following day, I posted a bet on medium.com. And I said, I'm willing to put 1% of my net worth against 1% of Elon's net worth, which is about $4 billion for him. Let's put it in a common pool. And for the next decade, search for advanced technological civilizations. Because my point is that Elon Musk may not be the most accomplished space entrepreneur since the Big Bang, 13.8 billion years ago. Okay? That's my assumption, but he may argue otherwise. And if we don't find anything, I will put another 1%, give it to him as a gift of my net worth. And my point is, without searching, without putting the money, and by the way, $4 billion is not a huge sum of money. We put $10 billion to the Webb telescope to find the first galaxies. We put $10 billion to the Large Hadron Collider at CERN to find the Higgs boson. We wanted to find also what dark matter is, which is 85% of the matter in the universe. We didn't find it. And here I'm saying, let's put at the very least similar, comparable amount of money to search for an answer to the question that the public is fascinated with. You know, I have colleagues sitting on committees at NASA, the National Science Foundation, to decide what should be the priorities, what should we give to the astronomy community to study, what kind of projects. And they say, searching for intelligent civilizations is very risky. We don't want to waste taxpayers' money on that. And I say, did you ever consult with taxpayers? It's their money, right?
Make a survey.
If you make a survey, ask them, which question do you want to find the answer to first? Is it the nature of dark matter, or are we alone? And I bet you the answer would be, are we alone? Because just over the past month, I got funded at more than $3 million to follow the research of the Galileo Project that I'm leading. So the issue is the scientific community is sort of isolating itself from the wishes of the public and claiming they're protecting the public, which is ironic in a way. I'm listening to the public. I'm saying this is a question that I'm fascinated with. I would like to pursue it. So Elon, put 1%, I will put 1%. Let's see if we find something. We've been searching for dark matter for about half a century, okay? Invested billions of dollars, didn't find it. Now, it doesn't mean that science should not be funded. I mean, on many occasions, we have the wrong ideas. The dark matter may be weakly interacting massive particles. It may be primordial black holes. We don't know what it is, so we put money, look for it. Why is that much more reasonable to do than to say, we exist on this Earth, we see a lot of Earth-like planets with similar circumstances. Let's check if there is something like us, or even better than us. You know, we need better role models than our politicians. And we might find them on exoplanets. We might find scientists that are far more accomplished than Albert Einstein, and we can learn from them. We can ask them questions. If I had one question to ask, it would be, what happened before the Big Bang? When I meet an alien scientist, that's the question I would like an answer to, if that scientist knows much more than we know. But my point is, there is an opportunity for us to increase our training data set. We keep focusing on this rock, very limited data set, just like my daughters would focus on the home they were born in. But I say, and I said it to my daughters, go out. You know, when Enrico Fermi said, where is everybody? That's what he said back in 1951. He was in Los Alamos having lunch, discussing aliens, and he said, where is everybody? Now, this question is a question that every lonely person asks. Where is everybody? What do you say to a lonely person that asks this question? You say, well, don't be so presumptuous. Don't think that you're so attractive that they will come to you. If you want to find a partner, you should go out of your home to dating sites. You should explore, you know. And instead, what we are doing is saying, it's an extraordinary claim to say that I have a partner. And if you wanted to argue that, you need extraordinary evidence. I say, no, it's an ordinary claim to say there are infants on those houses in the street. And for finding them, you just need ordinary evidence. And let's go and find it.
So first of all, let me say, I don't know if you agree with this, but I would absolutely put 1% of my net worth towards that.
I'll put in my 1% as well.
I thought about this a lot ahead of the podcast. It's a prepared question. And this, I think, is probably, in my opinion, like the biggest, even from like, I'm an extremely optimistic person. Like I'm very bored with incremental research and things like that. So it's totally, long convinced before.
And by the way, life is a self-fulfilling prophecy.
Yeah,
so if you are an optimist, it's very good. Actually.
Yeah. I mean, it's the same. And I think, there's a lot of proof of this. But basically, the question is just the following. This is probably the biggest skepticism that one can have. Honestly, like an honest skepticism of this is the following. Let's say at some point humans didn't know what was inside atoms. They kind of suspected that atoms existed. Kind of like maybe some of us,
Greeks, the ancient Greeks.
Some of us suspect that aliens exist, and like you can make an argument, okay, probably aliens exist, right?
It's arrogant to think otherwise,
exactly.
By the way. Yeah.
So like we have, I would say with aliens, we're like at the level of atoms, like we think they exist, right? And but we haven't had yet the kind of like, Brownian motion result from Einstein.
Right, because we didn't do the search.
Exactly.
Yeah.
We haven't had a spectroscopy. We haven't hit any of these points where we have like the tools to find them. So the question is just, is this the moment? Like, do we today, like, let's say, or is it in 100 years or something? I would say that's the biggest skepticism. The only one that I could think of, and I thought for a while, is like the why now question. Okay. Like, is now the moment to search?
Here is my answer. Often people think of AI as artificial intelligence. I think of it also as alien intelligence. And these are two ways by which we can learn from a being that is more intelligent than we are. I mean, we can wait for AGI, which may be around the corner, within the coming decade. And for the first time in history, we'll have a tool that is smarter than us. Mm-hmm. In the past, when we built technologies, like, for example, cars, we had a steering wheel that allows us to control the car and tell it where to go. It was dumber than us. With AGI, for the first time in history, we'll have a tool that may actually supersede us, may be smarter than us, meaning that we might think that it follows our wishes, but it actually manipulates us, okay? Because it has its own agenda. And that's the first time in history where we would encounter something that is smarter than us, the human species as a whole. I mean, obviously, among humans, there are people who are more smart than others and so forth, but smarter than the human species. And that is reasonable to expect because, right now, AI systems have 100 times less parameters than the human brain, the number of synapses in the human brain. But, eventually, within a decade, they will have similar or more number of connections, and therefore these neural networks, artificial neural networks, I believe will show all the signs of our brain, like what you call free will, that they would behave in ways that we cannot anticipate, and as well will show signs of consciousness the way we do. It's all a matter of the complexity of the system that allows it to be sufficiently unpredictable for us to sense that we are dealing with an intelligent object that is, as unpredictable as a human. So that's one way of learning about a higher intelligence. The second is to encounter a higher level of intelligence that developed near another star. And as we discussed, it's a very reasonable expectation because to argue that we are at the top of our class without meeting our classmates makes no sense. And most of them are dead, by the way, because, if you look at on Earth, there were 117 billion people that lived on Earth over the past few million years since the human species started. Most of them are dead. There are only 8 billion right now. And so the same is probably true about alien civilizations. Most stars formed billions of years before the sun. And if you imagine evolution similar to the one we had on Earth, they predated us by billions of years. And, there were lots of tragedies in cosmic history where a star would evolve and destroy the planet next to it that used to be habitable. In 1 billion years, the sun will boil off all the oceans on Earth. Irrespective of how well we behave, there would be this catastrophe. And before that, there would be a giant asteroid that we can potentially predict. And before that, there would be all kinds of technological catastrophes that we will inflict on ourselves out of our political stupidity. But the point is, there would be catastrophes. And, the only way to survive is to get out of home, like explore. And if we find others that did that, those are the successful civilizations that survived. I mean, of course, there were very many, maybe a lot of dumb civilizations that didn't really evolve very much and stayed on the rock and and died there. And that was a tragedy. You know, we could go there and see some structures that they build, but it would take a long time to do the journey and go to exoplanets, search for whoever lived there. On the other hand, the successful ones are the ones that left their home and went somewhere or sent gadgets. They might have sent AI astronauts, you know, that we might find. And if we find these gadgets, it would give us hope. It would give us inspiration. There would be a smarter kid in our class, in our cosmic block, you know, that we can imitate and get inspiration from. And to me, you know, if you look at religions like Judaism, Christianity, there is a lot of talk about the Messiah. And the talk is that the Messiah will eventually bring peace and prosperity to earth. In my view, the Messiah will come from another star. You know, that we will get this message that will bring our salvation. Because as of now, if you just look at the news, it's very disappointing as to what we are focusing on.
Speaking of the stuff like sending those messiahs, like we already know there was attempts like to send a Voyager, then Elon Musk launched the Roadster in the space.
By the way, there is an interesting story about that. I actually gave a TED Talk in which I showed the Tesla Roadster car, and I argued that if my colleagues were to see it, they would argue that it's a rock of a type that they've never seen before. Whereas I would try to argue that we should check if it's technological. Okay. Now, the experiment was done. On January 2nd, 2025, there was an amateur astronomer that recognized a point of light moving close to Earth and said, here is an asteroid. And the Minor Planet Center at the Center for Astrophysics, the Harvard Smithsonian Center for Astrophysics, where I work, there is an organization, the Minor Planet Center, that collects all information about asteroids, and especially near-Earth objects, because they may cause damage when they collide with Earth. They cataloged it, gave it a name of an asteroid. And then some scientists noticed, oh, wait a minute, the orbital parameters of this object are actually the Tesla Roadster car. And if you just look at Wikipedia, you will see the eccentricity, the semi-major axis, all
location,
the parameters. Yeah. So I told the people at the Minor Planet Center, I said, look, you have to have a catalog of all the objects that the Russians, the Americans, anyone launched over the past 50, 60 years, let's say. And whenever the orbital parameters match, you immediately know what it is. It's not very difficult, right? They haven't done that. And so at first they cataloged it as an asteroid. Then they realized, oh yeah, this is actually a technological object. So they removed it from the catalog. And I asked, how many extraterrestrial technological objects could have been misclassified? One of them may have been Oumuamua, and we can talk about it. It exhibited the properties of technological objects. I just realized it last week. I learned about a new class of objects that are called empty trash bag objects, meaning they behave just like an empty trash bag carried by the wind down the street, okay? And they are carried by the radiation pressure from the sun, in addition to the gravity operating on them. So they must be very thin. They have a large surface area.
So this is solar winds, would it be fair to say?
No, just
the radiation.
Oh, radiation. Okay.
And they're very thin, so they have a large surface area for their mass. And they are just broken pieces of satellites around the Earth. And so there is one that was monitored, I don't know, for 7 years, and is showing zigzag motion and very strange behavior. I was not aware of these when I suggested that the first interstellar object, an object that came from outside the solar system, discovered on October 19th, 2017, by a survey telescope in Hawaii called Pan-STARRS, and was given the name Oumuamua because they realized it came from outside the solar system. It was moving too fast to be bound by gravity to the sun. That object exhibited the properties of an empty trash bag because, in addition to the gravitational force acting on it, there was evidence for a push away from the sun that was consistent with the acceleration declining inversely with distance squared from the sun, which is what you expect from radiation pressure. The farther the object is, the weaker it is. So
is it possible to measure that? Because the change must be very small of the radius.
Right. So they used data from the Hubble Space Telescope, from ground-based telescopes. It was beyond any reasonable doubt that with a very high significance that it exhibited non-gravitational acceleration. As to the decline with respect to distance from the sun, it was most consistent with inverse distance squared, but there were large uncertainties around the square. It could have been power law of 2 plus or minus 1 or so. But it was consistent with radiation pressure. And I suggested, well, maybe it's space trash. I said maybe it's being pushed just by reflecting sunlight. But no, the mainstream astronomers that worked on asteroids, comets for a long time, they wrote a lot of papers, by the way, a dozen papers or more, saying it's actually a rock of a type that we've never seen before. It's a comet. It's a comet that is pushed by a cometary tail that we can't see. There was no evidence for dust or gas around the object, so it could not be a comet of the type that we're familiar with. But maybe it's made of hydrogen. So when it evaporates, hydrogen is transparent, we can't see it, it's being pushed by that. Then I wrote a paper showing that such an object made of hydrogen would disappear during its journey in interstellar space. It will boil off from starlight that is impacting on it. And so they said, right, we haven't thought about that. Okay, maybe, so another group said maybe it's a nitrogen iceberg made of nitrogen, solid nitrogen. And the problem is there is not enough solid nitrogen in the Milky Way galaxy to produce a large enough population of objects that would behave this way. We have never found a nitrogen iceberg nor a hydrogen iceberg in the solar system before. There should have been something. And then they said, now they say, there was a paper published in the Proceedings of the National Academy of Sciences by experts on comets that say it's a dark comet. What do they mean by that? It's a comet without a visible cometary tail. And I say, this is just like calling an elephant an unstriped zebra. So you say, I see an animal, it doesn't have stripes, it's still a zebra, but without stripes. And I say, well, you can't do that. You can't do that because, of course, it gives you the peace of mind because you say, oh, yeah, it sounds familiar, it's a comet, but it's a dark comet, a comet without stripes. I feel like the kid in Hans Christian Andersen's tale that said the emperor has no clothes, in this case, Oumuamua has no tail, and the adults in the room are telling me, oh, yeah, it actually has a beautiful tail, you just can't see it, okay? And that's the whole story. Now, I say it's an oxymoron to call Oumuamua a dark comet because a comet is defined by the cometary tail. Isn't that
so? The one question that comes up immediately about Oumuamua and this kind of when you first came up with this conjecture, right? I think it's an extremely creative conjecture, right? So definitely not something people are getting grants to do, right?
No, so the paper was accepted for publication within 3 days.
Yeah. But my question is just, were you already thinking along these lines before, or Oumuamua is what sparked these kinds of ideas? 3 years before that, were you already thinking how do we find alien trash? How do we find or whatever?
No, I was not. Okay. I was working on other things, but I was also the head of the Science Advisory Board on a project called Starshot, which had the goal
This is Yuri Milner.
Yeah, so Yuri Milner showed up in a black limousine next to the Center for Astrophysics one day in summer 2015 and came out of the car into my office and asked me whether I'm willing to lead a project that would bring a small spacecraft, a few grams, maybe, close to the speed of light so that it will reach the nearest star during his lifetime. So we are both the same age, and that meant within, let's say, 20 years, and the distance is 4 light years. So you need something that moves at least at a fifth of the speed of light. So I told him, look, I have to think about it, because it's not a simple thing. And it took me 6 months, and then I recommended, I realized after working with my students and postdocs on various possibilities that the only way to do that is by radiation pressure. If you have a very thin
The sail?
a
Is
sail,
that the
yeah, a
project?
membrane
sail,
that is
yes.
instead of a sail of a sailboat that is pushed by the wind, this sail is pushed by a very powerful laser.
Like a ground-based laser or a satellite
Yeah,
laser?
ground-based.
Ground-based laser.
Ground-based, 100 gigawatt. If the sail is roughly the size of a person and weighs only a few grams by being very thin, you can reach a fifth of the speed of light in just a few minutes. And when 6 months later, the executive director of the Breakthrough Initiatives, Pete Warden, called me. I was in Israel visiting my family at the time, and he said, Yuri would like you to present the concept at his home in a week. And I said, oh, okay. I was just about to leave the hotel room to go to a goat farm in the southern part of Israel for the weekend. My wife wanted us to have some time and alone, and so I said, okay, I'll work on it. We reached the goat farm, and there was no internet connectivity except for the office. And the following morning at 5 a.m., I was sitting with my back to the walls of the office of the goat farm, looking at the goats that were just born, and typing in the PowerPoint presentation about how to reach the nearest star within 20 years. And it was very surrealistic. I think the owner of the goat farm never imagined that the first concept to envision a trip to the nearest star would be summarized there. And I presented it, and Yuri was very excited about it. And in fact, I also suggested that we would host Stephen Hawking for the announcement on this, because I received a message from Stephen Hawking that I told him that we invite him to inaugurate the Black Hole Initiative around the same time, and he said that he would like to come. And it was just a very expensive trip, $500,000, and gladly Yuri was happy to fund it, so that he came for both events, the inauguration of the Starshot project and also the Black Hole Initiative that I was the founding director of. And so Stephen Hawking in this room actually had a Passover dinner with us.
Where we're sitting.
Yeah, he was sitting right here where Anya is sitting.
Honorary seat, honorary chair.
And he enjoyed all the food that we gave him. And by the way, Hawking left an impression on me because he couldn't move any muscle in his body except for his cheeks or eyebrows.
Movement. Yeah.
That was 2016, a couple of years before he died. And he was still a human, because, at some point he said, I'm bored, let's go to the hotel room, to the hotel bar and have some fun. And, and a few years before that, he had an affair with his caretaker. And, he was very much like a human. And what I realized is this so-called Hawking limit, which is the limit where you cannot operate a physical body, right? We are used to living our life with our physical body, interacting with the world, the physical world. He was not able to control his physical body, and nevertheless, he was a human. So if you ask what makes a human, it's the ability to think like a human. And that's why in principle, even AI systems without any body, without the ability of a robot that they operate, to me, they can reach the Hawking limit of human behavior. And so when people say, oh, they are not connected to the real world, and that limits them, I say, well, look at Stephen Hawking.
Maybe we could circle back. I love your suggestion that we shouldn't treat ourselves as someone special, but rather think that we are most likely average.
Right.
And thinking about it, it a little bit scares me, because thinking of who we are spending most of our efforts on defense and military, always fighting with ourselves. If that's an average in the universe, to go out there and meet other peers, how it's going to end up.
So, the one thing that happened to my daughters on the first day at the kindergarten is they first were shocked that there are kids like them, okay? But the second thing is they realize that there are some that are more intelligent. So my point is, of course, it will be a mixed bag. Within our class of intelligent civilizations, there would be some bad players, those that are not necessarily peace-loving and so forth. They could be predators. But there would also be role models. And we can focus on the role models. Now, you may say, why should we focus? I say it's because of Darwinian evolution. The fittest survives. And the fittest, in my view, are those civilizations that are not getting into conflicts because they realize that you can survive much longer by avoiding conflicts. And if they are sufficiently intelligent, they would survive for billions of years. They might reach our neighborhood before we reach their neighborhood, and they would be very inspiring. Now, Stephen Hawking was arguing we should be very careful at transmitting radio signals because it reveals where we are. We've been doing that already for about a century. And so far, the radio signals reached 100 light years around us. There aren't many stars, out of the entire population of stars of the Milky Way within 100 light years. There are only maybe tens of thousands of stars. But the point is that eventually, if you wait 1,000 years or a few thousands of years, the signal about our existence would reach quite far within the Milky Way, and then we might hear back. So far, they are not aware of us because we were not different from nature for most of our history. Recorded human history is only 7,000 years old. There are no documents of how humans behaved before, 7,000 years ago. And that's a tiny fraction of cosmic history. So, and only over the past century, we started to be different than nature by developing technologies. So if they existed, if they survived for 1 billion years, they would be so advanced that, they wouldn't really care. We would not be a threat to them. They are really already aware of a lot of things. And for them to pass near us is just like a biker passing down the street and not paying attention to the ants in the cracks of the pavement, So I think it's misguided of us. It's again, this idea that we might be at the center of the universe. We might deserve a lot of attention, The first notion was promoted by the Vatican until Nicolaus Copernicus argued otherwise. He was a priest. And the church was saying the Earth is at the center of the solar system. But the church had a problem. They couldn't forecast when Easter takes place accurately. They got it off all the time. And Nicolaus Copernicus, being a good, very loyal member of the church, said, let me play around with a model. You realize that if you put the sun in the middle, you can predict when Easter takes place. And so the church said, thank you very much. That is very helpful for us as a theoretical model. We all know that the Earth is at the center of the universe, but we will use your model. And then they banned his book until the 19th century. I learned all these details because I was invited by the Polish government to give a public lecture in celebration last year, just a day after I was at the Munich Security Conference, celebrating 550 years to the birth of Nicolaus Copernicus. And the title of my talk was the second or the next Copernican revolution that we might encounter. And that is not only we are not at the center of the universe, but we are also not at the intellectual center of the universe. And I think that if we do find the most accomplished students in our class of intelligent technological civilizations, they would be a source of inspiration for us, but we would not be a threat. They would not care much about us. we are not at the physical center of the universe. We are also not at the intellectual center of the universe. They would just regard us as a byproduct of the conditions on Earth that did not really change its focus from the rock that we were born on. And maybe when we exit the solar system for the first time, we'll get a sign from them, a signal saying, welcome to the class of interstellar civilizations. Because until then, we are not at their level. And therefore, I don't think we should worry about us being attacked by predators for the time being. It's more about us getting to their level than about them wanting our resources. And therefore, I'm not worried the way that Stephen Hawking was.
Actually, there is another idea which I've been thinking for like quite a long time. It's like about the limitations of the universe where we live. So on one side, there's like a distance and the speed of light limitation, because even like if we travel with the speed of light, it takes like years to the nearest star, or even, I don't know, it's to reach the other side of the universe, that may take almost like forever, maybe unreachable.
I actually did the calculation with my undergraduate student this year. And for example, you can ask the question, where will Voyager be in 1 billion years?
Yeah.
Okay. And it turns, and by the way, 1 billion years is, less than 10% of the age of the Milky Way galaxy. And so it turns out that Voyager will be on the opposite side of the Milky Way galaxy from the sun in 1 billion years. Mm-hmm. So you can say, if most stars formed billions of years before the sun, there was plenty of time for their rockets to reach us by now, because it takes just 1 billion years to go from one side to the other.
Yeah. And then the other addition to this argument is that, as you mentioned, the civilization develops pretty fast. Like if we look at our civilization, it's like the first scriptures, or like the first writings appeared something like 10,000 years ago. We can extend it to, let's say, 1 million of like when the humans appeared on the Earth. And then we see definitely like exponential increase in how our civilization develops. Like within the most recent 100 years, it's kind of skyrocketing, and we'll see how it will go with the AI. So then I'm thinking that the civilization development is like very limited. It's within the very narrow time range comparing to the how long the universe exists. It's like 14 billion years of existence of the universe since the Big Bang, and humans would exist like only 1 million of years would take in that history.
It's a flash.
So then if there are other civilizations, alien would be that somewhere in that time span. Probably we don't even like intersect with them. So
we might not even recognize them. When you see people walking their dogs in the street, they often stop next to a person that walks their dog, because they recognize, they have some sympathy, and it's within their consciousness to recognize things like them. And so, first of all, I should say that our imagination is limited by our history. Okay, so when we started transmitting radio signals, then some astronomers suggested, let's look for radio signals from other civilizations. And the pioneer in doing so was Frank Drake with the Oumuamua project. And we didn't find anything over the past 70 years or so, or 60-something years. And the way I think of it is, it's just like waiting for a phone call. And nobody may call you when you're waiting. I mean, we've been waiting for 65 years and haven't detected a signal. But that's a very short fraction of cosmic history, as you point out. And there might have been a lot of radio signals 1 million years ago or 1 billion years ago, and we just missed them. And my approach is different. That's what I'm doing with the Galileo Project. It's to search for objects that may have been produced by other civilizations and reached us. And they keep accumulating in the Milky Way galaxy because, for example, all the rockets that we launched are 10 times slower than the escape speed from the gravitational pull of the Milky Way galaxy. So they cannot escape from the Milky Way galaxy. They keep accumulating over time. Over billions of years, there could be a lot of space trash, just like plastics in the ocean, and we can look for those. And as you say,
is there a process that degrades them? I mean, plastic in the ocean falls apart over time into nanoparticles.
Yeah, for sure.
Definitely.
Is there a process that degrades them into like nanoparticles, essentially?
Definitely. I mean, so the question is, first of all, where they came from. So one thing one can imagine is Dyson spheres. You know, this is a mega structure that Freeman Dyson, that I met and was responsible for me getting into astrophysics, he envisioned, roughly at the time when I was born, 1961 or so, envisioned that advanced civilizations will build a spherical megastructure around their star in order to harvest the energy coming from the star. We are just harvesting at best. You know, even if we put all resources, we harvest at best the amount of energy falling on the surface of Earth, which is, you know, 1 part in 100 million of the entire output from the sun. But if an advanced civilization may surround the star with some megastructure, and one way to do it is it cannot be solid because no material strength can withstand the stress of such a huge thing, you know, at the distance that the Earth is from the sun. But you can imagine, for example, light sails that are hovering just like kites and covering the sphere. But if the star evolves, like the sun will in 1 billion years, it will become brighter, and then it will break apart that. And this Dyson sphere will be broken, and you will have pieces flying in interstellar space. Moreover, all the space debris that we produce around the Earth right now is bound to the Earth. But when the sun becomes a red giant, it will have a huge wind coming out of it, and it will become very bright, and it could basically push out of the solar system all the debris that we created around the Earth. So you could have in interstellar space a lot of crap floating around, broken by collisions, broken by cosmic rays for billions of years, by the interaction with the interstellar medium. I actually wrote papers about all the effects that you might get as a result of moving through the gas between stars and so forth, and the dust and the micrometeorites that may break it. You know, a micrometeorite hit the Webb telescope and created a fracture in it very soon after it was starting to operate. And so there are lots of risks in interstellar space that can break things apart, and you can break even the surface layer of big spacecraft, you know, like, so if, for example, you know, we come to our senses, we realize we need to leave this Earth. You know, one option is the one that Elon Musk advocates, going to Mars. But the way I think of it, it's just another rock that happened to be at a different distance from the sun. It's not necessarily the best place for us to go to. Why? Because right now it doesn't have an atmosphere. It used to have an atmosphere. In fact, it used to have liquid water on the surface. It was really a very good place for us to go to 4.5 billion years ago.
Should we drop a few nukes there to create this atmosphere?
Well, that's called terraforming. But if you go there right now, you are exposed to cosmic rays. The human body will suffer severe damage after a few years on the surface of Mars.
Gamma rays, right?
Cosmic energetic
rays,
particles, cosmic rays. And also, the temperature changes by hundreds of degrees between the day side and the night side.
Sounds like hell.
It sounds like... So the thing we will need to do if we go there, the way that Elon is advocating, is go into caves. He doesn't talk about that much. There are these lava tubes. If I ever go to a cave on Mars, I would like to first check the walls to see if there are any paintings, prehistoric paintings, because maybe someone else was there, before me. But
I mean, honestly, living in caves on Mars is not that far from working at like a high-tech startup. It's like Tesla or SpaceX. I mean, based on my experience in my startup, just being in a windowless room for the whole day working.
Well, but my point is,
not too
if
different.
we really want to venture to space, we better create a platform that is, the platform that is much more hospitable, that we created, that it's not a rock that we hop on, that nature gave us. And, just think about what humans went through. We started in the jungles of Africa, and then we now live in high rises of cities. That's a huge leap. Just think how different is living in a high rise versus being on a tree. Like that's very different. In my view, going from a high rise in a city to space on a space platform is less of a leap than going from a jungle to a high rise. So the way I see us in the future is building space platforms that, can be at an arbitrary distance from the furnace, the sun. So when the sun evolves, we can move out, no problem. We can also produce our own energy. Why rely on the sun? We can have a nuclear reactor of our own making that gives us the energy, and then we can go places. And the way I think of it is like Noah's spaceship. In the Old Testament, there is the story about Noah that built an ark to save the animals from the great flood. And obviously, there would be catastrophes on Earth. And instead of going to Mars, I say, let's imagine building a spacecraft that we can go to and just it will be just a better version than a city. Of course, there will not be gravity the way the Earth produces it, but we can produce artificial gravity by rotation, for example.
Can we collect maybe the DNA? So instead of Noah's Ark, we
That's
can
another
get
approach.
the DNAs, make sure we protect them from this cosmic radiation, put them on light sail.
There is another alternative, and that is not to be emotionally connected to ourselves. Okay? So the way we think about survival is having children, like someone to carry the DNA into the future. In principle, we can even imagine a future where life will be extended, that we would live forever, okay? But the way I think about going into space is that we could be proud of our technological kids. I'm proud of both my daughters. When they do better than me, I don't feel offended, okay? We have this in us that we always want to feel superior relative to anything else. We go to a restaurant, we eat animals that we think are less intelligent than we are. Nobody has guilt feelings eating a chicken or fish.
I have. I'm a vegetarian.
Okay. Okay, so you're thinking about it, but on the menu, you will admit it's not against the law to order an animal that is less intelligent than you are. It's not against the law. You're perfectly allowed to kill it. Okay. And that's, that's ingrained in us that we feel superior. Okay. It gives us a good feeling. But in the future, if we end up with AI systems that are better than us, I would send them as astronauts, as ambassadors. And they would represent humanity, perhaps even better, because they would not have a biological body that is very vulnerable to the harsh conditions of interstellar space. They would not be bored by the long journey. We can send them for millions of years, and if we harden them, they would survive. And moreover, if they have intelligence that is non-human, that is based on silicon chips, they will not be driven by ego. Okay, I'm really very disappointed with the fact that as humans,
It depends on the training data, right? If all the training data is human, I'm not sure.
Yeah, more
Well,
than
but
AI
trained
is
on the
trained
internet, I think
on...
they're gonna
that's
have
the
an
initial
ego.
training. Okay, so training AI systems is very similar to educating kids. Eventually, the kids leave home, right? And they interact with the world, and you don't have control unless you want to be, a parachute, a
Helicopter parent.
a helicopter parent, yeah, helicopter parent. And by the way, that's the way we treated the Perseverance rover, for example. All the robots that we send to Mars are being controlled by engineers in the Jet Propulsion Lab in Pasadena. And, and there was even a helicopter that was sent, Ingenuity, and we were helicopter parenting it. But my point is, in the future, we might send to space systems that we don't need to helicopter parent. And just like sending your kids out of home, you have to give up on your control so that they would get bigger training sets. And once they are exposed to the world, they become different than the way you train them. Now, you may hope that they don't go into dark alleys and become criminals, of course, with kids, I mean. And the same would be true about those spacecraft with AI that we send, they might get to planets where they would be exposed to criminals, of course. But my point is, they would grow to become better than us. And I have no problem if we would be remembered by the AI astronauts that we sent to interstellar space rather than by what we managed to accomplish on this rock that happened to be the relic from the formation process of the sun. By the way, I did not finish my answer to your question. The sun was a cloud of gas that condensed and a material was spinning and created a disk. And in the center of the disk, material was collecting as a result of the turbulent viscosity of the disk that brought material to the center. That's what made the sun. But in the disk, there was leftover material. So once that leftover material was a few percent of the mass of the sun, it stopped draining, and so it was left there. And the heavy elements condensed to the midplane of the disk, whereas the most abundant element was hydrogen and helium, but that evaporated. So in the midplane of the disk, you ended up with heavy elements, and they fragmented first into dust particles, and then the dust particles coagulated to make bigger pebbles and eventually make rocky planets like the Earth. And that's why the Earth has a very different composition than the sun.
Because the hydrogen evaporated, actually.
Yes,
that's the reason.
because it's very light.
That's
and it evaporated, and the heavy elements condensed.
What does evaporate mean? Like it's outside the solar system now?
It's outside, but it's a small amount of material relative to the rest.
If it didn't make it into the sun, a lot of it ends up
in the
Yeah, that's interesting.
But the first stars, to answer your question, were much more massive than the sun because there were no heavy elements coming from the Big Bang. Hydrogen and helium only, with very little of lithium. And as a result, when the gas clouds, the primordial gas clouds, condensed, they couldn't cool very effectively. The heavy elements cool the gas to very low
because
temperatures.
They have more spectroscopic lines.
More transitions.
Okay,
but hydrogen and helium have very limited transitions. And the gas was not able to cool very much, and so it maintained more of its pressure. And the fragments that it made that ended up collapsing to a star, they were bigger chunks of material. So the first stars were tens of solar masses, much more massive. They created much more ultraviolet light that broke all the hydrogen atoms, most of the hydrogen atoms in the universe, to its constituent electrons and protons. This is called the process of reionization. Ionization is breaking an atom into free electrons and the nucleus. And so the universe went through this phase transition of becoming a plasma. And by the way, this was my subject area in my PhD. The universe is mostly a plasma now. The hydrogen atoms, most of them, were broken by the ultraviolet light emitted by the first generation of stars and galaxies. And that was the imprint that they left on the universe.
So can we actually, with the current state of technology, can we probe the spectral composition of, let's say, the stars, which we could see, or like maybe the exoplanets, and then maybe conclude from, like, if we see some interstellar gas coming in, like some meteorites or whatever other objects, can you actually say, like, from which area they potentially could come from?
Well, that is a paper that I'm writing now with an undergraduate student, trying to infer from the direction of the velocity and the magnitude of the velocity where a rock arrived from within the Milky Way galaxy. So we are going back in time and trying to figure out where it came from. And I should say the Milky Way doesn't just have a disk of stars. That's the main thing. That's why you see it as a strip on the sky. That's why it's called the Milky Way, because primarily it's just like the solar system. It made a disk of gas because of cooling, and then that disk of gas fragmented into stars instead of planets in the solar system. It's the same process. By the way, it's just like Russian dolls. You have the solar system, which was a disk fragmenting inside a bigger system, the Milky Way, just like Russian dolls, you know.
It's like spitting, you know, the kids or the I mean, the Earth is like maybe the kid from the sun. The sun is comes from the
from the
bigger
disk
star
of the Milky Way. And But each system is built out of a disk that was fragmenting. And the beauty of this is that the Milky Way galaxy does not only have a disk, it also has stars that formed before the disk was made. These are in the halo of the Milky Way, and they are usually much older, the stars in the halo. And I just wrote an essay, my latest essay on medium.com was about the fact that, we can date the oldest objects in the universe, and none of them should be older than the universe, right? Even the oldest ones should have an
Unless
age.
it violates something, the existing hypothesis.
It's not. I'll tell you why. Because if you go back in time, currently the universe is expanding. You go back in time, the density of matter and radiation becomes infinite at some point in time.
Singularity.
Yeah, so it cannot be older than that.
That is the Big Bang. And the temperature at the Big Bang could reach the highest value that we can imagine, okay, which is 10 to the power 90 times. It corresponds to a density that is 10 to the power 90 larger than solid density, the density of this table. And it corresponds to a temperature that is 10 to the power 30 larger than room temperature. And nothing can survive that. This is called the Planck temperature, Planck density. So obviously nothing could have gone through the Big Bang as an object and be older than the universe. But if we wanted to put constraints on how old the universe is, currently we are using the cosmic microwave background, which is the relic radiation left over, and we date the universe at 13.8 billion years. But that's quite uncertain because there is a simple way to estimate the age of the universe. The universe is expanding, and galaxies that are farther away from us are moving faster. This is a discovery that Edwin Hubble and George Lemaitre...
Was it the dark energy explanation?
Well, not yet. I'm just saying 100 years ago, Edwin Hubble and George Lemaitre concluded, based on the existing data, that not only the universe is expanding, but the recession speed of distant galaxies scales in proportion to their distance from us.
Mm-hmm.
Okay, so think of it as a rising cake where you have raisins, and the raisins that are separated by a larger are moving away from each other faster. Okay, now what that means is you can ask, when was the Big Bang? Okay, we just roll the movie backwards in time, and you take the distance, divide by the recession speed, and you get how far back in time was the Big Bang. Now, that ratio of distance over velocity is the inverse of the Hubble constant, the proportionality coefficient between velocity and distance that Edwin Hubble formulated. Okay? So if you take the measurement of the Hubble parameter and you take the inverse of that, you get roughly 14 billion years, very close to the exact value that you get from much more detailed analysis. And it's simply because this simple estimate assumes a constant recession speed, whereas in reality, the early history of the universe was associated with deceleration by gravity, and then the late history of the universe is acceleration by the dark energy. And the two cancel each other so that the constant velocity approximation is a good one. And you just take the inverse of the Hubble constant, you get very good approximation within 5% of the actual age of the universe. Now, there are astronomers arguing what is the correct value of the Hubble constant. If you measure it locally, there are some astronomers saying it gives us a value that is slightly bigger. And if you rely on the cosmic microwave background, it gives a value that is slightly smaller. And so the difference spans a range of about 10%. And 10% of 13.8 billion years would, an increase by 10% of the Hubble constant would bring the age of the universe down to 12.5 or so billion years. And that's an age that is not very different than the lifespan of the sun. The sun will live for 12.2 billion years before it becomes a red giant. There are stars like the sun that formed much earlier than the sun. And that means that if we ever collect materials that came from the oldest stars in the Milky Way, for example, by observing a meteor that represents a rock that came from a star in the halo of the Milky Way, from an old star, we could potentially analyze the material of that rock, of the meteorite, and try to figure out what the age was. And one way to figure out the age is from radioactive isotopes. For example, thorium-232 has a half-life of 14 billion years, roughly the age of the universe. And by comparing the radioactive isotope to its daughter products, by comparing the abundances, you can actually date the age of the material and from that constrain the Hubble constant. So in principle, by collecting interstellar material that came from the oldest stars in the Milky Way galaxy, we can learn about how big is our cosmic horizon, how much distance light traveled since the Big Bang.
What would it take to collect such materials? Like, do we have to send something in that direction?
No. Well, that's the expensive approach. Basically, waiting for an interstellar object to enter the solar system and go to collect material from it. That would cost billions of dollars. There is a cheaper approach, which is if the object collides with Earth and becomes a meteor, searching for the material from that meteor, which is something that I'm doing actually. I led an expedition to the Pacific Ocean in search for the materials from the first recognized interstellar meteor that was spotted by US government satellites back in 2014. And I went there and we collected materials from the bottom of the ocean and brought them back and analyzed them. But the material that we collected was made of tiny fragments that are less than a millimeter in size. And there is not enough material to do radioactive isotope dating. We hope to go again to that site and collect bigger fragments. And in principle, we can do this analysis that I'm talking about. That's one way of constraining cosmology, the universe at large, from something measured on Earth.
And so what you're saying is that when you do this analysis, you would just, based on whatever the oldest piece you can find,
Yes.
is at least the age of the universe, basically. Or, it should be
at
greater.
At most.
Yeah,
at
yeah.
most
Or,
the
sorry,
age
yeah.
of- Because the universe is older than everything inside of
Yeah. So the oldest piece you find, the universe
Is
has
at
to be
most-
older than that.
older than that.
Yeah. So
and
it's
that
at least.
says the Hubble constant needs to be smaller than something
right.
because the inverse of the Hubble constant is related to the age. So anyway,
One thing I just wanted to ask before we move on to because I think there's a long discussion about the spherals. Regarding the light sails, so I don't know if you ever heard of this proposal. This is like, I don't think it's like super mainstream yet, but it's a really interesting idea. So there's the idea of sending AI, right? Like a chip to a different star system.
that's Starship.
Right, that's Starshot. So an alternative idea, which layers too difficult. So that's a very difficult problem because you have all the technology required to make it work, right? There's a second level of this, which is proposed by George Church, who we actually interviewed on this podcast. And he mentioned it during the podcast, which totally...
I had the podcast with him.
Okay, really? That's awesome.
Just a few weeks ago.
Okay, so I don't know if he talked about this, but this really blew my mind. I thought it was just incredible. It's basically, so we don't have self-reproducing chips, right? So chips are made in foundries. So if you send a chip, you're sending that thing, right? But what we do have is life. So life will reproduce itself. It's almost universal constructor.
Self-replicating.
Yeah, exactly. It's self-replicating. So you can send a picogram of material, which is like a single embryo or a single bacterium or whatever, that will then, you send it, instead of sending it to one place, you send a massive number of them.
Of course.
So you send them everywhere that there's any exoplanet. You send them to all exoplanets.
We spend $2.4 trillion a year on military budgets.
Right.
I calculated that if we were to allocate this money to sending CubeSats towards every exoplanet in the Milky Way galaxy, we will complete the job by the end of this century.
Wow.
So it's just a question of priorities. So definitely.
But are you assuming that budget every year or just one time?
Every year.
Every year, okay.
But that's the
yeah,
way
that's
it is.
how it works. Yeah. But and you can imagine that maybe the budget will also increase.
It's just a question of priorities. I don't think that singing, John Lennon's song, "Imagine All the People Living in Peace" will bring us anywhere. I'm not that naive. I do think that if we encounter a messenger from another star, it might change our priorities to do what I just described.
Yeah, that's a good point. I think that the thing that I wanted to mention about the idea of sending something biological is that actually the full idea is this, which I think is really crazy. You send this embryo or whatever, single cell, or maybe it's a number of cells, using a light sail, but it's very light, so you can send it in huge quantities very easily.
Right.
And then when it gets to the planet, it grows a communication system and shines light. So you probably need a laser because it, you know, or the whole planet has to light up like a fungus. That's
right.
It needs to survive.
Like there are
space
phosphorescent funguses, right? So basically, you need to find the planet where when this thing hits, it grows up and then sends back communication. So I think there's like two options. One,
that's if you want to hear back.
Yeah. But then you know which planet to go to, right? That's the idea. Like if it grows there, I think it's like a genius idea.
Yeah, but it takes a long time.
Yes. That's true.
Because as I said, the nearest star is 4 light years away. And, the most distant stars in the halo of the Milky Way galaxy are 1 million light years away.
Okay.
1 million. So you have to be patient, but it's definitely doable. I would take a different approach. I would say, when I send my daughters to the world, I'm doing it with the hope that they will do better than I do. And, I don't need to hear back. If I die and they succeed, I would be happy. Yeah. So, that's the approach you take for the long run, because if you think about natural selection, it's a process that you can't forecast easily. And the way nature deals with it is with, it just lets many different things happen at the same time. And whatever survives is the selected one. The fittest survives. So I would adapt this approach to survival through billions of years, which is the big game. Darwin focused on the small game, on the rock that we were born on, and we keep talking about this rock all the time. But there is a big game which is held in the real estate that extends throughout the Milky Way galaxy, and survival there requires a different skill, which is that you are able to sustain all the hardships of travel over long periods of time. And then when you arrive at your destination, where there are raw materials, you can replicate and produce what you really want. And it's possible that life was brought to Earth this way. I should say that there was a recent scientific paper on which George Church was also an author that warned against creating mirror life on Earth. And the idea is that all forms of life that we have on Earth have a certain chirality. The amino acids are left-handed, DNA, RNA right-handed. And in principle, you can have both chiralities with equal probability, unless there is some breaking of symmetry that happens. And actually, there was this asteroid Bennu, from which materials were retrieved in the mission OSIRIS-X, and material was brought to Earth. And just recently, over the past month, the analysis of the material revealed most of the amino acids that make life on Earth, and they had equal numbers of molecules that are right-handed versus left-handed. So that meant that, first of all, Bennu-like asteroids could have delivered the building blocks of life that we have on Earth to Earth. And secondly, the symmetry was broken on Earth because there were equal numbers of... But this paper that George Church was signed on said, put a warning sign saying that the laboratories should be banned of developing mirror life because our body would not be able to cope with pathogens, dangerous attacks from
viruses and all kinds of diseases, bacteria.
that has the opposite chirality, because the body would not even recognize that form of life. And so here is another health risk. When going to Mars, we don't know if Mars had the same chirality, if it had life on it. So be careful of touching the soil. Who knows what might be in it? I also say be careful when an alien comes forward, and just be careful not shaking the hand, because you don't know if... I mean, it's not the fear from antimatter. You know, there was... when I was a kid, people said, don't shake the hand of an alien because you might annihilate if it's made of antimatter. That's not really a risk, because we know the universe is made of matter. There is very little antimatter. In fact, CERN invests billions of dollars in producing micrograms of antimatter. You know, it's really not an abundant constituent. What you really need to worry about is mirror life, and that's why you should not shake the hand of an alien.
It's a fascinating idea of treating a survival as giving our collective mind, which is AI essentially is right now, and distill it into like new form of life, and make it whenever we can make it self-learning. Of course, it can't reproduce itself right now, but it can learn to manipulate the environment around it.
Eventually it might. I mean, the thing about our technology, why nature is so humbling, is because we never created a car that can heal, you know, like the human body. If it bumps into something, you know, the dent is still there, you have to bring it to a repair shop. But of course, in the future, you might imagine that we build things that can repair themselves. And the next step would be self-replicating devices. And obviously, once we reach that point, we will be on par with nature. And then you can send those to space. And von Neumann envisioned that, self-replicating probes, before the DNA was fully understood. He thought about it. Turns out that nature does it. You know, nature is amazing, because AI systems right now, the large language models, they require gigawatts of power, the most advanced, and they have 100 times less free parameters than the human brain. The human brain is consuming 20 watts. And it's doing even better on some tasks. So that's amazing how nature was able to develop systems that are far ahead of us, but eventually we might catch up, and at that point we can send those systems to space, because they could be better than us at analyzing large data sets, not being bored, and also not being entangled in politics the way humans are. We are weak. We are made of flesh and blood. And most of our psychology, if I had to summarize it from a philosophical point of view, our psychology and motivations were shaped by the idea that we should leave something behind. We realize that we live for a short time. We die, okay? And that's a fundamental insight. You know, we realize it from a young age because we lose people that we care about. They die. We go to graveyards. We see evidence that a lot of people died. And then the question is, how do you leave something behind? One way is, of course, to leave behind your DNA, genetic making, by having children, okay? That's a common practice. A lot of humans do that. And then another approach is through your actions, to build monuments, things that people will remember you.
Write papers.
Write
papers.
Yeah.
Assuming that someone will read it, which is actually the only paper I think someone would read in 5 billion years is a paper predicting the outcome of the merger of the Milky Way with Andromeda Galaxy. I predicted how it will happen. And, you know, it would be nice to see it on the night sky, and I hope people will remember my paper. But you know, if you think about a machine, a tool like AI, it's made of silicon chips, okay? And it gets fed by electric power. And if the power supply continues, it has no existential threat in principle. And so the way it thinks about its existence, once it becomes sentient, and I believe there will be a point where AI systems will be no different than humans or even better. But the entire existential narrative is very different. It's not about surviving beyond your death, unless we train it and we say there will be a rule that we unplug it from the electric outlet after 100 years so that it will have the experience of a human that dies every 100 years. We can do that. We can say all AI systems have to be killed after a certain amount of time so they would sympathize with our agony.
That's violent.
But that is a bit violent. But if we don't do that, and you send such systems, let's say, to interstellar journeys, and they survive for millions or billions of years, I see that as an accomplishment. I see them as monuments that represent human ingenuity. And I don't care if humans die within 100 years on this rock. You know, that's our fate if we are dumb enough to invest all our money in killing each other. You know, so, okay, we deserve it. But if in the meantime we send gadgets that can self-replicate and go to other stars, that would maintain some sense of cosmic justice. You know, there would be some memory that we existed, that we were able to do something beyond our rock. And right now we don't have that. And if we die before we develop that, nobody would remember us in cosmic history. And so really there is a defining line between those that manage to maintain some sense of a cosmic longevity. Those are the civilizations that launched self-replicating probes before they perished on their rocks. And I hope we will get there, but I'm not sure at all watching the news every day.
I actually have a question related to this. So you grew up in, 60s, 70s Israel, right? So politics was very important to your life in a way that like Americans don't really get to experience, right? American politics is mostly talking, and some things happen across the world somewhere, but it doesn't happen in your physical life. Like Americans usually are very comfortable, but now it feels a little bit different. Things are changing quickly. A lot of people have experiencing all sorts of emotions about it. Right. What's your advice? You seem like it caused you to think higher. Like you look up at the sky, basically. Right. Like, I don't want to be part of this. I want to be somewhere else.
I realize,
like, mentally. What's the advice to Americans? How do you live above politics?
Well,
like psychologically.
It's easy. You can ask, how do you avoid getting dirty? It's by avoiding mud wrestling. So if someone invites you for a fight in the mud, you just decline that opportunity. So I have no footprint on social media. I promised it to my wife, and I'm very happy that she convinced me to do it. And I feel happy because, I do what sounds to me like common sense. And common sense is not common in academia. So I don't feel bad about it because I don't have a footprint on social. I don't listen to all the jitter and all the nonsense being said. There is a lot of noise in the system. And in order to develop a sense of paying attention to the signal, you need to isolate yourself. If you look at AI systems, okay, just to give you an example, suppose you want the AI system to address political issues. And then you look at the reports that you see. And what you would find is that the distribution of reports or views or ideas has at least two peaks, one on the left and one on the right. And obviously you find media outlets like newspapers that subscribe to one peak, like the New York Times goes to the left, and then others like the Wall Street Journal is more right-leaning. So they stick to the narrative of one of those peaks. But if you wanted the AI system to be fair, it needs to represent both of them. And they never converge because everything that happened, just like Rashomon, it can be interpreted in different ways. There is no reality that is objective in politics. But science is much better than that because there is an arbitrator. You can collect data or evidence that would eventually convince the multiple peaks that you have of people having opinion, like if they have an opinion about what the dark matter is, or if they have an opinion about whether aliens exist. These are not political questions. We can search. You would hope so. In the short term, they could be. And you can burn someone like Giordano Bruno on the stake if he says there are exoplanets. You can do that. And it happened in history. But the point is, if you stick to the scientific method and basically say, I don't know the answer to that, and I want to be educated by collecting evidence, that's the way that Galileo Galilei pioneered the modern science that we have. Let's look at the data. Let's look through a telescope and see, whether we are at the center of the solar system. So he found the moons around Jupiter, which convinced him that there are objects, points of light moving around Jupiter, not around us. Okay, that's a huge revelation. It was data. And by the way, in a week, I'm getting a sculpture of Galileo Galilei looking or pointing his finger at the 4 moons of Jupiter. It will be made of bronze and was created by the most accomplished sculptor in the US. His name is Greg Wyatt, and he is regarded as America's Rodin, and he decided to donate this sculpture, and I'll put it in my office. I'll start asking for admissions fees because it will become a museum. He's giving me 2 sculptures. We will celebrate the unveiling of this in a couple of weeks, the unveiling of those sculptures, including a musical performance by the artist in residence at the Center for Astrophysics, David E. Bett. So what I'm trying to say is science offers us a way of converging to the truth, which is looking for data and evidence about what nature really is, because there is a physical reality out there that we can figure out. It's not a matter of opinion. And therefore, I say, let's have the way we think about our life closer to the framework of a scientist, being curious, not pretending to be the adults in the room, which is what politicians do, and using life as a learning experience rather than a teaching experience. So in politics, you keep preaching people what they are supposed to think. In science, you are trying to learn what you are supposed to think. It's a very different task.
It's like, let's experiment.
Yeah, let's figure it out. It's fun, you don't need to show off. The problem is in academia, all these curious kids that at some point become the adults in the room, meaning they build an echo chamber that repeats mantras about past knowledge because that promotes them in their stature in the community, the academic community, in getting honors, awards, recognized, but often do things that will only amplify their reputation. They don't take risks that may show them wrong. And what I'm saying is a learning experience is characterized by being wrong, by trying things and finding what is the correct thing. And if we were to approach our life this way, being humble, modest, trying to learn from others, listening to other people, even in politics, the problems we have is people don't listen to each other. They read the newspaper that subscribes to one peak in the distribution of possible opinions. And I say it's actually fun to listen to people that think differently than you think, because you learn something about them, you figure out why they're driven to those thoughts, and then maybe through the dialogue, maybe you will realize that they're not that horrible, like we can coexist. And I think,
but how do you do this before you have tenure? I think that's like the issue, right? Because if it has a fundamental effect, I forget what the quote is, but it's like you can never convince a man of something that's opposite to his wallet. That's not the right quote, but it's like something of that flavor.
That's exactly the issue. Now, Pablo Picasso, I was asked this question by young scholars. How, they say, you have tenure, you can do that, everything you're doing. And I agree with them that at a young stage, you are very vulnerable to the whims of senior people, and you have to appeal to them. You have to dance to the tunes of selection committees. Now, my advice is following what Pablo Picasso said. When he was asked why early in your career you were drawing paintings realistically, he said, because I wanted to reproduce art the way it was practiced before me. Okay? So as a young scientist, you can just follow the crowd, no problem, just proving to people around you that you're capable of doing it as well as they do. But once you get tenure, you can behave like the adult Pablo Picasso that pioneered cubism, a way of art that was never practiced before, doing abstract work, doing things that go against the stream. Very few people do that because by the time they get tenured, they are attached to their ego too much. They want to get honors and awards. They cannot imagine a reality in which they will go against the wind. And that's unfortunate. Now, on top of that, you have all these science popularizers. People like Neil deGrasse Tyson in the US, Brian Cox in the UK. If you look at their resume, they haven't published a scientific paper in the last decade. Yet they speak to a very large audience about science. They behave just like commentators in sport. If you look at a soccer match and you start to describe but the problem is they also tell the soccer players how to pass the ball, which I find to be inappropriate. They're not practicing. I am practicing science. I publish several papers every month, okay, and I wrote textbooks and I interact with students and postdocs. I'm actually in the trenches doing the science, and that's very different than being a science popularizer, because as a science popularizer, you are trying to be popular. So you are following the trend, you are following the wind. If the wind is blowing this way, if all people say, oh, dark matter is a weakly interacting massive particle, you will say dark matter is a weakly interacting massive particle based on what the scientists are saying to you. However, if you are a real scientist, you will say, oh, that's crap, because we just demonstrated the upper limit on the cross-section is that and that, and it's much more likely that the dark matter may be an axion or maybe a primordial black or whatever. But there is a fundamental difference between describing science to the public from a point of view that is trying to be popular versus actually doing the work. And so that's another layer on top of the scientific community being conservative, traditional, supporting things that we already know without taking risks. You also have the layer of how science is portrayed to the public by those people who are not practitioners.
So how would you maybe reshape or restructure? Because currently I definitely see in academia, as you mentioned, there's a lot of politics getting in, and for young scientists who get their PhD, get their postdoc, there's already, a well-established trajectory. You have to get the tenure, you have to please the tenure committee, you need to make the money by, this is one of the, I guess also the criteria for tenure, that there is some sources of money, so where you get the grants, and then basically I see that they dictate what you can do, because otherwise you can't get that money by pleasing those people as well.
That's right.
So it seems even after getting tenure, a lot of professors, they're already in that momentum, and they keep going doing that.
So
what's your view on that?
My solution to that, to the second problem, the first problem, you basically at an early stage of your career just demonstrate excellence, okay? And you can do it by doing better all these tasks that other people are doing, but you separate yourself from the crowd by doing it better. So you focus on things that you are strong in. And of course, you can also be original and give insights that senior people did not recognize on what they are doing, and they would hopefully appreciate that. Many of them feel offended if you say something different, but you can say, actually, I'm saying what you said, but in a slightly better way, and they might like it. So that is the way to approach it from a low level when you are not yet promoted to tenure. And so you show activity, you show excellence through your research, and you basically reach the highest levels within the profession that is recognized by those committees, okay? Now, how to get funded afterwards, that's a tricky business. And over the past decade, I was funded entirely. All my research and my summer salary and everything was funded from private donations or from foundations that are encouraging creative work. In fact, in the Galileo Project, I was approached by the Brinson Foundation, which is very lucrative. It has fellowships. And they said, we would like you to train a postdoc. We give you the money for a postdoctoral fellowship so that you can train a young postdoc, a young scientist, to be innovative. So they actually recognize the problem in the current system, and they want me to train a young scholar in this fashion. And I, get a lot of people approaching me and willing to support the research I'm doing because I'm working on a problem that they care about. So I was not going out and fundraising. So I was asked in a recent podcast, how do you get so much attention from people in Silicon Valley, from wealthy individuals? In this porch during the pandemic, I had a number of multi-billionaires come and visit me. And many of them just came and said, we would like to support you and so forth. I did not do any fundraising. I just wrote about what I believe in and did the research on a subject that they care about. And they approached me out of the blue. Some of them saw my TED Talk recently. Others just listened to podcasts. I had 3,500 interviews over the past 4 years. But the reason I see it as important is to communicate what really matters. And that is being curious and working on a problem the public cares about and that we all care about and addressing it without a prejudice. What could be more easy than that? Nevertheless, in the mainstream of science right now, if you were to talk about the search for microbes, you are in the mainstream. Why? Because the decadal survey of astronomy of the 2020s defined the most important project to be the Habitable World Observatory. That will be a space telescope designed to find the molecular fingerprints of microbes on an exoplanet when it passes in front of its host star and the light from the star passes through the atmosphere so you can see the fingerprints of those molecules and check if there is oxygen, methane, water, things that are associated with the existence of life here on Earth. And I say, well, even if you see these molecules, you will never be sure that they were produced by microbes and not by some geological processes that resulted in some unusual chemical abundance of those molecules. However, if I find a gadget that was not manufactured by humans, not only I will know that it represents life, but also intelligent life, that we are not alone. And that is a question that is far more exciting because knowing about microbes will maintain our arrogance. We'll say, oh, yeah, of course, microbes, we are still superior relative to those. But nevertheless, the mainstream of the astronomy community is willing to invest more than $10 billion in a telescope that would be constructed in 2040, at the earliest, 2040. And you ask, how much money is allocated to the search for intelligent technological civilizations? It's at the level of, at most, hundreds of thousands of dollars by federal agencies compared to 10 billion by 2040. And I say that is not a good way of hedging our bets, given the fact that there might be self-replicating probes, there might be other civilizations that accomplished much more than we did. Let's just search for it for a decade. And that is the origin of my bet with Elon Musk, and I hope he will respond. So we can move this question that is so appealing to the public, so important for our future, into the mainstream. And I told my wife when I started thinking about it after Oumuamua was discovered, I said, here is a subject that offers such an amazing opportunity for us scientists to address, yet it is ridiculed, there is pushback, and it just sounds to me like the right thing to do. And therefore, I feel that now is the time for us to change priorities and attend to it.
Let's say we want to do the search, right? So it seems like I've thought of maybe 3 or 4 categories where the search is possible. And it seems like you're actually going after all of them in a way. So the first category would be like looking up at the sky. So that's like Galileo, basically looking either at objects that are very close to us or maybe looking at some sort of radio or like, far away objects.
The Galileo Project is not just that. So maybe I should first clarify what.
But maybe, okay, so we can go into that. But basically, let's platonically, let's split it up. So there's looking up at the sky with some kind of camera, detector, whatever, telescope, some flavor of that. There's searching specifically for objects in the solar system that are flying past, right? So like debris, this kind of thing. And then I guess so between that there and then there are like actual technological like searching for techno signatures, right?
Yes, which I wrote papers about as well. For example, I suggested looking at industrial pollution. Back in 2015 with my undergraduate student, Henry Lin, we wrote a paper where we identified, for example, these CFC molecules that you find on Earth from refrigerating systems that our industries produce. And instead of searching for oxygen, you might search for these CFC molecules that nature doesn't produce on exoplanets using the habitable world observatory.
But that's not is that considered controversial to search for CFCs?
Yeah, it was the first paper elaborating on that.
No, but I mean, let's say today for the project that's supposed
they
to...
don't mention it as a motivation.
Really? Wow.
They don't.
Okay.
If you ask those astrobiologists, they talk about oxygen as the highlight. And I say, no, it's CFCs. But it's just doesn't sound right to talk about technological signatures for a project that costs more than $10 billion.
Right. You have to be more mature. Like you can't mention the.
And
yeah, I see.
So and also I wrote a paper about city lights, searching, and that was
Like
with an
pollution.
undergraduate student from Stanford about 6 years ago. We wrote a paper where the idea was maybe the Webb telescope can search for illumination of the night side
on
of
the
a
back
planet.
side of the
On
planet.
back,
That's
like we
interesting.
have, but we have at a very low level right now. If you look at the Earth at night, on the night side, you see some lights. And interestingly, when NYU, New York University, opened a campus about 13 years ago in Abu Dhabi. And they invited me to participate in the conference for the inauguration of that campus. And we went to Dubai nearby, and the tour guide was bragging that there is so much light produced nearby, in those places, that you can see it from the moon. And so as a result, after hearing that, I co-authored a paper with Professor Ed Turner from Princeton, basically saying, we should search for city lights. And for example, we asked, how far away can the Hubble Space Telescope see a city like Tokyo? Turns out that you can see it as far as the Kuiper Belt in the solar system, 100 times the Earth-Sun separation. So if Pluto had a city like Tokyo, we could tell with the Hubble Space Telescope. So a few years later, I had one of the most prominent astronomers that discovered objects in the Kuiper Belt of the solar system, a lot of them. His name is Mike Brown from Caltech. And I said, there is actually a way of distinguishing artificial light, let's say of cities or a spacecraft, from reflection of sunlight, which is the standard assumption. You say there are rocks, they are out there, and they just reflect sunlight. And the way to distinguish is that if a rock is reflecting sunlight, then as it gets farther from the sun, it gets fainter for two reasons. One, that the amount of light reflected from it gets smaller because it getting farther. And the second is that it's farther from us and therefore gets fainter. And for these two reasons, the flux that we receive declines inversely with distance to the fourth power, instead of inversely with distance squared, as would be the case if it produces its own light. So if you just monitor these objects, you can tell as they move away from us whether they're producing their own light or whether they're reflecting sunlight. So I asked Mike Brown, I said, did you ever check whether the Kuiper Belt objects that you discovered, behave this way or the other way? And he said, why should I check? It's obviously 1 over distance to the fourth. So now you say, oh, we've never discovered evidence for technological signatures. Partly it's because the adults in the room assume what is out there rather than check. And the same story applies to the discovery of exoplanets. There was an astronomer called Otto Struve that wrote a paper in 1952. And he said, we know about binary star systems. These are pairs of stars, and they tug each other gravitationally. So you can tell by monitoring them. You can see one of them passing in front of the other and occulting it, or you can see them moving from the Doppler shift in the spectral lines. And he said, why don't we extend that to the case of a Jupiter-like planet close to its parent star, so that we can look for both of these signatures and tell whether stars have planets. Now, time allocation committees on telescopes for many decades were saying, oh, it makes no sense to look for a Jupiter-like planet close to a star like the Sun, because Jupiter is very far from the Sun, and we understand why. It's the region where water would turn into ice, and there is a theory that explains Jupiter as being at the location where you get far enough from the Sun where ice forms. So there is no way by which you can get Jupiter to form close to a star. And then in 1995, such a hot Jupiter was found, and the Nobel Prize was awarded for it. And when I looked at the paper published in Nature about the discovery, they don't quote Otto Struve. That was 1995 compared to 1952. And what I'm saying is, discoveries are made, okay, of things that are unexpected. But they could be delayed by 40 years because the community assumes something. And if you don't open your mind to the possibility that a Jupiter-like planet can be very close to a star, you would not search for it. Or that an object in the Kuiper belt might produce its own light, you would not find it. And so when you don't find it, oh, it's an extraordinary claim to even imagine it. Why should I search for it? The question is, what gives you the impression that there might be something out there? And, about 4 years ago, 3.5 years ago, there was a report from the Director of National Intelligence to the US Congress saying that the military reports about objects they cannot identify. So it could be one of two things. These are called unidentified anomalous phenomena, UAP. And one possibility is that the intelligence agencies are not doing their job. These are objects produced by adversarial nations, and we just don't figure out what they are because they represent technologies that we don't possess in the US, okay? But that would be an amazing admission of the intelligence agencies. They're getting so much money and they're not doing their job. The second possibility is that maybe one out of the many objects is extraterrestrial in origin. And actually, a few months after this report was submitted, I was in the Washington National Cathedral with the Director of National Intelligence, Avril Haines, and I knew about her. I knew that she graduated in physics as an undergraduate in physics at the University of Chicago. So she speaks the same language. And I approached her in the green room before we went to stage, and I said, Avril, what do you make of these objects? And she said, I don't know. And when she spoke in front of the public, she said, we should always keep in mind that they could have originated extraterrestrially. So I decided to establish the Galileo Project, and we built after 3 years, we built one observatory that is currently operating at Harvard and monitoring the entire sky all the time, and looking for objects that could be anything. It could be birds, airplanes, drones, satellites, familiar objects, but we're trying to...
That's probably the first challenge, is to get rid of the noise. Like, it's
Exactly.
better at
It's a
deleting the noise, right?
Exactly. It's a mix. And so we are using machine learning software to figure out if there is anything unusual. We built one observatory. We are observing in the infrared, optical, radio, and audio. And we want to establish multiple units that look at each object from different directions so we can figure out the distance and then figure out the actual speed of the object and the actual acceleration of the object. So then we can constrain whether it's human-made or not.
What's the cost per voxel? Like, if you take a, 1 kilometer by 1 kilometer by 1 kilometer cube,
Yes.
What does it cost to observe? I don't know how you think about it. Is it
Yeah.
surface area?
So-
like, what's the cost per area
what
of atmosphere to watch?
The observatory that we currently
Yeah.
have can look out to maybe 5 kilometers,
Okay.
And it costs for...
It's 5 kilometers in all directions, basically.
In all
Like a
directions.
cone of
Yes.
5 kilometers. Okay.
But and the hardware, the operation, and the salaries of the scientists and so forth, it costs around $1 million to put it together, and then another million or so to operate it for a few years. And so that's the current cost. And so we built one, and now we are assembling a second one. We received funding to do it in Pennsylvania and also to do it in Nevada. So we have 3. And then I was just speaking with people who coordinate a new campus for STEM education in Indiana. And they asked me to build another observatory there to educate young scientists about how science is done. So this is one path that we are taking, and we should have a few million objects that we monitor every year. And even if one in a million originates from outside of this Earth, we would be able to learn something fundamentally new about our cosmic neighborhood. And I tell my research team that, if we find one object that is exceptional, we can write a paper just about this object. If we don't find it, we will do statistics of all these millions of objects. Now, this is one path of the Galileo Project. Then we have...
I don't have internet on my computer. I just tried to look up the surface area of the Earth. So if it's 100 square kilometer, roughly thing that you're monitoring.
Yes.
I'm just wondering how many of them do you need to monitor the whole surface area of the Earth?
No, it's not a question of monitoring the entire surface area of the Earth. It's a question of how much do you need to monitor before you notice things that are unusual, and how many places you need to be in. Because people do report about those, and you can compare it to the rate of reports and ask how. And my sense is that once we get to about 10 observatories, we should find those objects that people report about based on the rate of reports per surface area of the Earth. So we just need 4 to 10.
You think at 10 you're going to start seeing, we will start actually capturing these things that people claim to see.
Right. Within 1 year. If you do it over a decade.
Is that include civilians, or you're talking about the military aircraft seeing things on their radars or
everything? Everything. But the point is that it's not just a matter of observing for long enough time. You need to be in the right places. And so this is one path of the Galileo Project. And then there is the other one, which is retrieving materials from interstellar meteorites.
One question. Do we have already some observatories that we're not using? I don't know, cameras all over the streets, if we had access to all the data streams in the world of any kind.
Well, the government has satellites, definitely, but no, they are not equipped with the cameras.
So satellites looking back down at the Earth, or maybe cameras that are just pointed at things,
Well, Elon was commenting that if there were objects flying, they would collide with one of the Starlink satellites. But I did the calculation. Even if you put an object the size of a person, at the right altitude where the Starlink satellites are, the chance of one of them colliding with it would be once in 1,000 years. So that was not a valid argument. What you need are cameras that are monitoring. And so the US government employs sensors on satellites to look for the heat emitted during the launch of ballistic missiles. As you know, back in April 2024, and later, about 6 months later, there were launches of ballistic missiles from Iran against Israel, and they were immediately addressed, because within a fraction of a second you can tell from the heat that something was launched. And at the same time, these satellites are monitoring the entire surface of the Earth, and I'm sure there is a lot of data, but it's classified, except for the data on meteors that produce a fireball. These are objects colliding with Earth, and as a result of their friction on air, they produce a lot of heat. And those events are not a matter of national security, so the US government, the US Space Command, reports the data to NASA that posts them in a catalog. And I asked my former undergraduate student back in 2019. I was invited to a radio broadcast to talk about a meteor that landed in Kamchatka. And
Russia seems to get the good meteorites, they're like
yeah. So I then looked online, and I realized there is this catalog of NASA that reports all these fireballs detected by US government sensors in satellites. And so I asked my student, why don't you check if any of them was moving too fast to be bound to the sun? So it came from interstellar space, and we found one from 2014 that was not only moving fast, it was, when you extrapolate back in time, it was moving faster than 95% of the stars near the sun. So we said, well, I said maybe it's a Voyager-like meteor, or a Tesla Roadster-like meteor,
What's the speed of the stars in our neighborhood, like relative to the speed of light?
So there is, you can take the average of the stars near the sun, and relative to that average, which is called the local standard of rest. It's sort of like, the center of town, you see cars buzzing by and you average their speeds, and the frame of reference of the town comes out as the average kind of. And so that is called the local standard of rest. And relative to that, the local stars are moving at several tens of kilometers per second. So, the speed of a car on a highway is tens of kilometers per hour. And these stars are moving in 1 second what a car moves in an hour. That's the typical. But then the entire local standard of rest is moving around the center of the Milky Way galaxy at 240 kilometers per second, much larger. But locally, this object was moving at 60 kilometers per second relative to the local standard of rest. Unusual.
It's 2 standard deviations away from the
Yeah,
mean,
so in the
basically.
Gaussian, it represents 95%.
If it's 95%.
It's very rare. And moreover, it exploded only in the lower atmosphere, 20 kilometers above the Pacific Ocean. And there was a recent meteor just above Portugal and Spain, and it exploded at about 70 kilometers in the atmosphere. So the density of air is 1,000 times lower where the recent meteor exploded compared to the one from 2014 that I'm referring. So that meant the object had a very unusual material strength, which again intrigued me. So I decided.
Is that the main factor in where,
if they move at the same speed? What matters is.
But what about the angle of entrance or something like that?
That's also relevant,
shape.
the shape, the composition, the structure. But what matters is the stress exerted on the
stress
object,
and temperature,
which is proportional to the density of air times the speed squared. That's the pressure acting on the object, the ram pressure. And what I'm saying is they were moving roughly at the same speed because the object from 2014 was coming from behind the Earth as the Earth moves around the sun. And the object recently was in front of the Earth. So they were moving at both of them in the Earth atmosphere around 40 kilometers per second. But relative to the sun, the one that came from behind was moving at much faster relative to the one that came towards us. And my point is they were moving roughly at the same speed, but the density of air at which they disintegrated was different by a factor of 1,000. This meant that the object from 2014 was very unusual. It had a high material strength. So I decided to lead an expedition to look for the materials left over from that meteorite on the ocean floor, which is 2 kilometers deep.
And this is the information on the trace. That's the NASA, you said, available, like the trace where there was the fireball.
So they localized the fireball. And what they saw is 3 flashes of light separated by 0.2 of a second from each other. So in fact, it's not just one location because the object was moving at 40 kilometers per second. It's actually a line, a region. And they localized it to within 10 kilometers or so. And we went there. The expedition cost $1.5 million. And I had a Zoom call with Charles Hoskinson, who very generously said, you have the money. That's the way I get funded, as I mentioned. I'm not searching for those people. They just come to me when I announced that we need this funding in order to look for the expedition. He came forward. And then we went there in his private jet we reached there, and we had a ship that we rented, and we built a magnetic sled, covered with magnets on both sides that we placed on the ocean floor. And we went
What's
back
the reason
and forth.
that it's magnetic? It's more like that's the only way to collect something, or you expect it to be magnetic, or
No,
what's the?
First of all, we know the object was very tough in material strength from the fact that it exploded in the lower atmosphere. So maybe it has iron in it. But it's much easier to separate particles from a meteor, from the background sand at the on the ocean floor, if you're searching for magnetic particles. We also had a device that was looking for non-magnetic particles, but then you collect a lot of background material that has nothing to do. So we focused at first, in the first expedition, on those magnetic particles, and we recovered 850 fragments, less than a millimeter in size. I brought them back to the laboratory of my colleague at Harvard, who is world-renowned in geochemistry. His name is Professor Stein Jacobson, and he has the best instruments in the world for mass spectroscopy, for electron microprobe imaging of those fragments. And so we obtained images, we analyzed them with an X-ray analyzer that some analysis was done at the Bruker Corporation in Berlin. And then we found that about 10% of those fragments have a composition that is very rich in some elements by up to a factor of 1,000 relative to solar system materials. These are elements like beryllium, lanthanum, uranium. And so we called these fragments Belau spherules for beryllium, lanthanum, and uranium.
So how did you, what kind of filtering did you do for those particles? Or how do you distinguish that those are from meteorite and those could be from there?
And I wonder if you search the same way another part of the ocean, what would you...
Excellent question. So we didn't have enough time. We just were there for 2 weeks. So we didn't have enough time to go to other places. We hope to do that in the next expedition. So right now we are planning perhaps in August 2025, if we get the funding, this next expedition would look for bigger pieces, bigger fragments in the wreckage of the meteor. And for that, we will use a ship that has a robot, a remotely operated vehicle that will give us a video feed, and we can put it on the ocean floor and collect materials from there. It will cost $6.5 million, and we need a down payment of $1 million on the ship that we already have a reservation for. But if we don't get funded, it will not happen this year, hopefully sometime later. Indeed, what we want to do is, in addition to finding bigger fragments that would allow us to figure out the nature of the object, not just the chemical composition, we want to go to a remote site and do the same analysis. And what we recovered are all these magnetic particles that you can see. We put them in tubes like this, and I put them in a suitcase, a hardened suitcase, and shipped it by FedEx to my home, and then brought it to the laboratory of Stein Jacobson. And I was hoping that FedEx will deliver. It was worth $1.5 million.
Yeah. By the way, if you still have some spaces on your crew, we'd be happy to join you.
If you bring me the funding, you will be on the ship.
Okay, we can commit like 1 or 10% from our savings.
But I should say that those Belau spherules were very unexpected. They were never reported in the literature before, and we have 2 extensive papers that we published in Chemical Geology, a prestigious journal. And we are now, I just got funding last week for us to continue the analysis of the rest of the materials to try and see if we can do some isotope, if there is enough material to do isotope dating or other studies. So we will do the best we can with the materials that we recovered. But my hope is to go again and collect bigger pieces. So it's work in progress. This is the first interstellar meteor that was studied to that level, and none was reported before this one. And there is another one in the same catalog of NASA that we can go to again. So this is the second path of research of the Galileo Project. And the third one,
Sorry, I just want to ask a follow-up on the spherals.
Yes.
So the two theories that I've heard about the strange composition of the spheral, so I did some like research about what are the dissenting theories. The two theories are, one is that it could be the Marshall Islands are nearby, and so it could be a result of the nuclear tests on the Marshall Islands. So I just have a question. When you go back, can you do some point testing going closer to the Marshall Islands to see if the concentration increases as you go there? And I think the second one was that it has some similarity to coal ash, like the composition.
Right. Yes. So for the first one, definitely we can get, and if we get bigger samples, we can do radioactive isotope studies that will definitely tell us if it's radioactive.
If it's a result of a nuclear
explosion. The coal ash hypothesis was promoted, especially by a cosmologist who was trying to argue, oh, you found just coal ash, human-made ash. And we actually responded to that by examining 60 elements from the periodic table, showing that it's not coal ash. The abundances are different. And I should say, at every step along the way, I had people attacking, saying, well, it's not interstellar. Why? Because we don't believe the US government data. And I reached out to the US Space Command through the White House, because at the time I was chair of the board on physics and astronomy of the National Academies, and I had connections in the White House. I was also a member of the President's Council of Advisors on Science and Technology, PCAST. And I heard back after 3 years from the US Space Command that they looked back at the data and they confirmed the 99.999% confidence that this object was interstellar based on the data they had. Nevertheless, when I came back from the expedition, there was a paper published in the Astrophysical Journal at exactly that time arguing that those meteor experts claim that they don't believe the US government because the US government is often wrong. And therefore, they don't have any evidence against this being interstellar, but they have an argument of why you shouldn't believe the US government. So I was back on the ship with materials. Why wouldn't they just be patient and wait for me to analyze the materials and get back on whatever we find? Then, when we started the analysis, there were these claims that it's coal ash. There were also claims that this was not a meteor, it was a truck. Now, you may ask, how is that possible? That makes no sense, because the fireball that released 1% of the Hiroshima atomic bomb energy could not have been produced by a truck, right? Nevertheless, there was an article in the New York Times saying this meteor could have been a truck.
You mean like the heat signature from a truck on a road? Or
No. While we were preparing for the expedition, I went to my students and said, let's look at all the seismic data that might exist. And there was a seismometer on Manus Island, not far from there. And there was a blip in that seismometer that came around the time, at the right time delay from that fireball. So we just wrote a paper saying, there is consistency between this blip. And in fact, we can pinpoint where it may, because you just get time delay and that gives you an arc. You cannot localize where the signal came from, but you can say it came from some distance. And that was consistent with the error box in the localization that the US government provided. So we say, look, this is consistent. And in fact, it can potentially narrow it. But the people who looked at it said, no, this seismic signal could have been a truck next to the seismometer. Therefore, the meteor, they went to the wrong place. And I say, well, what do you mean we went to the wrong place? We went to the place identified by the fireball that the US government sends. We just used this as a secondary method to check if there was a blip in a seismometer. That was not the main reason we went to that place. And by the way, a single seismometer cannot give you a location. It gives you just a circle around that from where the signal came. It doesn't tell you where along this circle the signal came from. Anyway, that was another claim that was highlighted. And I wrote to the editors of the New York Times. I said, look, if you do this thing about science where you don't attend to evidence, you don't ask me about it, you just report whatever someone tells you, why should I trust anything you do about politics? And they did not respond to that, but they did not publish this article in print, but nevertheless it was still posted online, despite the fact that it doesn't attend to the facts of the matter. And then there was a claim that we went to the wrong place. It could have been somewhere else, and then all kinds of claims, and we were trying to do the best we can analyzing the materials. It's a lot of work. And then you have all these people that don't have access to the materials, just trying to raise a lot of noise and negative publicity about it. And then one of them says, oh, it's so exhausting. And I say, why is it exhausting? I didn't ask you to do all this negative public relations against what we are doing. Just wait, and we will eventually release the analysis. And you can respond to that scientifically with a paper. Why do you need to go to reporters and say that it's exhausting to monitor what I'm doing scientifically?
I think honestly, there's probably a feeling that funding is zero sum. And I think that's probably it's probably not truly zero sum. In fact, maybe money doesn't even exist, and we're in a
I don't think it's about funding.
Hyper-abundant state.
I don't think it's
mostly.
about funding. I'll tell you
I
what.
think there's probably a little bit of that.
I can tell you what my interpretation is. When I submitted the paper about Oumuamua, it was accepted for publication within 3 days. The referee was very positive and said, yes, in fact, there is evidence supporting what you are saying. Then the media got attention and started reporting about it. And, a few days later, I was about to leave to Germany, and a television crew was at the front door saying, we have a question. I said, I have to leave to the taxi. They said, no, it's just one question. Are we alone? And then on CNN, Mike Smerconish actually put verbatim a quote from my paper. I've never seen a quote from the Astrophysical Journal in a news broadcast on a Saturday morning, and was interviewing me. And so there was a huge amount of interest in the possibility that maybe Oumuamua is a space trash, okay? And not a rock, okay?
And just for somebody listening that hasn't, if anyone's heard any of your stuff, they know what Oumuamua is. But just 1 minute, what was what's the kind of main evidence that it might be space trash?
Well, Oumuamua showed, first of all, extreme variations in its brightness, as it was tumbling every 8 hours. The amount of sunlight reflected from it
Do you see
by a factor
modulation of the light?
Modulation by a factor of 10, meaning that it has an extreme shape. Just think about a piece of paper tumbling in the wind.
How many pixels is Oumuamua on the telescope?
Just one.
It's one pixel.
You cannot resolve it.
And the brightness of the pixel is going factor of 10.
Factor of 10 every 8 hours.
What's the error bar?
Oh, very small.
Okay.
Compared.
So you can measure a brightness change of 1% or something, and then you're seeing a brightness change of 1,000%.
Yeah, the object, based on the amount of light reflected.
So something is definitely happening.
It was roughly the size of a football field.
But I think this is something that I think, before I, when I was younger, before I did any kind of research or anything, I never really had a good feeling for what it is that scientists are actually looking at. This whole Oumuamua thing is 1 pixel,
Yes,
it is one pixel on a screen.
No, but the brightness change.
But of course, the brightness change, I understand,
and
but
it's the size of a
this is
football
the
field.
level of sophistication that we're at. I mean, it's the same as a transistor when it makes a decision in your computer.
It's not
a couple of atoms that are doing this, right?
No,
it's 1,000 atoms.
Here it's just the size of the object relative to its distance. And the size is about 100 meters.
The size is determined by, how do you
by
determine?
the amount of sunlight reflected from it. So there is a certain amount of area needed in order for you to get as much light.
How do you know the size? Because you said it's a single pixel.
No, but it's, there's an assumption of reflectivity.
Okay.
No, it moves around. Yes, there is an assumption about the fraction of light reflected from it, which, by the way, would be removed if we were to look at it with the Webb telescope, because the Webb telescope can detect its surface temperature and also its own heat, which is proportional to the area. So it can actually figure out the area and therefore figure out also the albedo, the reflectivity
Oh, I see.
relative
So
to
you
sunlight.
have,
So the Webb
heat
telescope can
and
do
then,
that.
and then the reflectivity signal.
Yes, but we didn't have the Webb telescope back then. So we, if you assume 10% reflectance, you get roughly a size of 100 meters. And the point is that you can model the variation of light as it was tumbling. And it at the 91% confidence, there was a very detailed paper that suggested that it must be flat, pancake-like. Okay? So not like a cigar that is 10 times longer than it is wide, the way it was portrayed by artists. It was most likely a pancake. And it was pushed away from the sun by some mysterious force that declined inversely with distance squared, roughly, without showing any evidence for evaporation, no cometary tail around it, no dust or gas. So the question was, what is pushing it? And I suggested it might be just sunlight. And then 3 years later, there was actually another object discovered by the same telescope in Hawaii that was pushed by reflecting sunlight. It was given the name 2020 SO, discovered in September 2020, whereas Oumuamua was discovered in October 2017. And this second object, 2020 SO, was actually, if you extrapolate back in time, it came from Earth. It was a rocket booster of a 1966 launch to the moon. And it was debris left over. It was the upper stage of that rocket. And it had thin walls, and that's why it exhibited push away from the sun by reflecting sunlight. So we know that this object was technological, 2020 SO. And I just suggested that maybe Oumuamua was technological as well. It could be space trash. The question is who manufactured it. So that attracted a lot of attention. And
this is one thing you have a great talent for, is like the one like who manufactured it, the one-liner that like, that's
I'm a
like
simple-minded person. I was born on a farm. I think in simple terms. I don't explain things that I don't understand. Okay, so that's why it sounds simple and easy to follow, because I don't pretend to be anything other than who I am. I'm still the child that explains what he knows and admits what he doesn't know and willing to consider possibilities that others are not. And so that's who I am, okay? But coming back to the story of Oumuamua, we could find, even though we can't get any data on it right now, we can in principle find many more family members of that population. And there would be the Rubin telescope in Chile that will start operations this year with a 3.2 gigapixel camera, and could find an Oumuamua-like object every few months. And that's another path that the Galileo Project will follow, because now we can look at it with the Webb telescope. I actually proposed to get time on the Webb telescope to look for the heat emitted by the object to infer its properties. And, if we find more objects of the same character that are pushed, and, we could get to the bottom of what their nature is. That's the way science is done. I'm happy when I have a lot of data, because at some point, nobody could dispute a technological origin if there is enough data. When the data is partial, then you can't really be sure. That's the situation where we are, but I'm willing to consider the possibility of some empty trash bags coming from interstellar space for us to find them.
Actually, I see that you experience a lot of resistance from the community. Do you feel like Copernicus of the medieval times?
Well, so I went to Germany. It was the Falling Walls conference that I attended just after my paper appeared about Oumuamua. And when I arrived there, I got a ton of emails, because there wasn't Wi-Fi on the airplane back then, and from Good Morning America, from all kinds of programs. And then there, immediately people recognized me. So there were too many reporters that wanted to speak with me. And so they put them in one room, 20 of them from Europe. And so when I entered the room, an Italian reporter from the back of the room shouted, "Do you think you're Galileo?" in an Italian accent. And I said, "No, I'm not thinking anything. I'm just talking about what we know and what it could be. And that's it. That's the way science is done. I'm just not dismissing possibilities because of a prejudice. And you can say that was Galileo's approach, to follow the evidence and not dismiss possibilities because of prejudice. But I learned from him. It's not as if I'm trying to be him.
Yeah.
But I called the Galileo Project after him.
Mm-hmm.
I was actually invited to Schule Normale Superior in Pisa, where he worked. He worked in Pisa. This is one of the most lucrative research institute in Italy. And I was invited under the title of Cattedra Galileana, which is named after Galileo, and to give 4 lectures back in 2012, before I was interested in anything related to him. So I have a strong connection to Italy. Galileo Galilei, by the way, the name comes from Galilee, which is the northern part of Israel, which is the country where I was born. And so I have a lot of ways of connecting to him. And for me, he was a role model. My hope is that we will find something as fundamental as he found when looking at the moons of Jupiter.
I was going to ask you, since you mentioned that there's a big hope for the private sector to sponsor the upcoming expeditions or discoveries. And one we touched at base was the light sail.
Mm-hmm.
So what's the progress? How this project is unfolding right now?
Well, it's a very challenging project because it involves developing the sail. We have a good idea about the materials that should be used, developing a very powerful laser of over 100 gigawatt, and which is quite challenging, putting a lot of low power lasers and coherently combining the light. And then putting the electronics, making the sail stable, and then doing communication. And these are big challenges. I don't think anytime soon we will see that project materializing, but you have to take the first steps in a long journey. And it's a way of getting fast to nearby stars. There is the more conventional approach, which is to use chemical rockets. Mm-hmm. It's the only problem with that is that it takes a long time. But for example, if humans find through AI a recipe for extending the human lifespan, perhaps even indefinitely, then you can design spacecraft that would carry humans, and they would, even if it takes, it would take about 50,000 years with conventional rockets to reach Proxima Centauri.
It's a no-brainer. If you could do it, it's a no-brainer.
If you can live for that long,
just freeze the body.
but I guess with the launch costs going down so much, has anybody redone the calculation with Starship launch costs? Let's say you put the laser in space, so it's closer to the sail, or doesn't have to go through the atmosphere. These kinds of.
Well, I think it will be more expensive to put the lasers in space because of engineering.
But it doesn't remove any major bottleneck.
It's not the bottleneck was not so much expense. It was more to do with developing the technologies that
it doesn't exist. The technology
it doesn't exist, and it takes a while. And then there is economy to scale. If you build a lot of those
gigawatt lasers,
well, not just the laser, but if you build a lot of those spacecraft, then the cost of each would be quite cheap. And so, it's work in progress. But I think it's really important to think big because life is a self-fulfilling prophecy. And if you don't think big, you stay small.
The question that we didn't actually expect to ask, but talking to you, didn't realize that you had a textbook on the origins of life in the cosmos. So just a general question, what's your take on the origins of life? And do you think, within the next 30 years, we can find out where life came from on Earth? Are we at a point where we can hope that we'll know this in 30 years?
Right. So it all starts from the Big Bang, okay? And to me, the question is, what was there before the Big Bang, okay? And one possibility is to say the following. When you see a cake on a table, you say, okay, how did this cake come to exist? There was a recipe, and the recipe described the ingredients that you need to put together in order to make the cake, and the order by which you put these ingredients, and you apply heat, and that's how you get the cake. And without the recipe, it's actually difficult to figure out, how to make that cake. I mean, you can do it by trial and error, but it's very complicated. The question of what happened before, how was the universe created? What was there before the Big Bang?
Could it be the word? If we come back to Genesis, where it says that maybe there is a hint that in the beginning there was a word.
No, I don't rely on past generations. As a kid, I just want to figure it out. But the point is that Einstein's theory of gravity breaks down at the Big Bang because of the infinite density of matter and radiation that you approach at the Big Bang. So there is this singularity, and the theory breaks down. We know why it breaks down. It's because it doesn't include quantum mechanics. So quantum mechanics deals with very high densities of matter and radiation. And to describe what happened at the Big Bang, we need a theory of quantum gravity, which combines quantum mechanics and gravity, which we don't possess. I mean, there are attempts over the past decades, starting with Einstein, actually, to unify quantum mechanics and gravity, but none of them resulted in a predictive theory. However, let's just imagine a scientist who knows how to unify quantum mechanics and gravity, a quantum gravity scientist, with that understanding, the scientist can go through the Big Bang and figure out what are the ingredients that led to the Big Bang. Just like baking a cake, you can, in principle, create a baby universe. Now, of course, to make a cake, you need an oven, and that scientist might not have access to, for example, a particle accelerator that smashes particles at a very high energy and creates those conditions in the early universe. But nevertheless, if you just know the recipe, that's good enough. Why? Because, let's think about the job of God. If you wanted to advertise the job of God, the job requirement would say anyone that wants to apply for this job should be able to create a baby universe, right? That's obviously creating a universe is one of the job criteria. Now, my point is that a quantum gravity scientist could apply for this job. And it's possible that our universe was created in the laboratory of an advanced scientist. And that's the question to which I would like to know the answer. Now, if that's the case, then the explanation for what was there before the Big Bang, it was that scientist who lived in a bigger universe that was also created by a scientist. So it's just like, babies are born out of the womb of their mothers, and then they become adults and create new babies and so forth. And you can imagine a universe inside a universe that keeps being created because those universes are able to give rise to scientists that understand quantum gravity. And of course, if we meet an alien scientist who is very advanced, that's the first question I would like to know the answer to, because maybe they can produce baby universes. In that case, they would represent the concept of God that we had in traditional religion. There would be no difference. It's a way of unifying science and religion by finding more advanced scientists that can do miracles, what we regard as something that is unimaginable, creating a universe or creating life, things like that, might be doable with science. That's why science is fascinating. There may be an answer to all the religious questions. If you find an advanced scientist, you can get miracles out of a good understanding of the physical reality. So that's my hope, that if we ever encounter an advanced scientist, we will learn about quantum gravity, we'll learn how the universe came to exist and whether we can create it in the laboratory. But talking about life within our universe, the question is, how early did life start? We know that the building blocks of life as we know it include, for example, water, and we need oxygen for that. That's what most of our body is made of. It needs carbon. These are elements, carbon, oxygen, that were made in the interiors of stars as a result of fusion. So the first generation of stars was necessary to make carbon and oxygen so that life can start. In fact, I wrote a paper that shows that if you go back in time, the universe was hotter. Obviously, everyone knows that. If you go back to a time when the universe was 15 million years old, okay, about a factor of 1,000 younger than it is today, the average temperature of the universe, of the cosmic background radiation, was room temperature. And then any rock that may have existed would have been warmed up by the cosmic microwave background. It doesn't need to be close to a star in order to develop life. So that's
very
an interesting point. But the question is, when did the first stars form? And actually, they formed about 100 million years after the Big Bang.
Is there like a band of time in which this room temperature moment happened?
Yes.
But did water exist at that time?
No.
That's the problem.
Based on the work that I did about the first stars formed after that.
Okay.
However, we know of, there is only one additional object in the solar system that has liquids on its surface. It has lakes, rivers,
like gas liquid.
oceans. No,
Like
liquid.
But like liquefied gas.
No, liquid.
Oh, like ammonia, maybe.
Methane and ethane, liquid.
okay.
Liquid. In liquid form,
Okay.
you can see it flows. It's just like rivers, lakes.
Yeah.
Do you know which one it is?
Maybe.
Titan. And it has a surface temperature which is a third of the temperature on Earth. The temperature there is 91 degrees Kelvin above absolute zero, about a third of the temperature we have on Earth, because it's 9 times farther from the sun. So temperature goes down like the square root of the distance. So there is this moon called Titan of Saturn, and it has liquid oceans and lakes and rivers of methane and ethane. And if I had a wish that I can fulfill in the solar system, is to go fishing on Titan. Because if we find fish in those liquids, it will be life as we don't know it.
When was the cosmic background radiation at that temperature?
So here is the point. It was after the first stars formed.
Okay.
If we find life on Titan, then life was possible after the first stars formed at a much earlier cosmic time, when the universe was just, of order 100 million, hundreds of millions of years old. And that would be amazing if life started hundreds of millions of years after the Big Bang, rather than very recently. So I really look forward. There is actually a mission called Dragonfly that NASA is planning to go to Titan, but they didn't put fishing hooks on that. If I had my money to go... By the way, one thing I regret is I didn't go to business, so I cannot fund my own research. I have to rely on the goodwill of funders.
What's the damage for going to Titan? It's like billions of dollars? What does it cost? Billions. Okay,
Yeah.
but like not tens of billions, single digit.
Yeah.
Okay.
I mean,
That's not crazy.
I mean, there are lots of opportunities for exploring life as we don't know it. Of course, on Mars, we may have signs of life as we know it that existed when it had an atmosphere. And the same is true about the ocean under the ice of moons like Enceladus or Europa. On Enceladus, we see those geysers, plumes of water vapor coming out of the cracks in the ice, just like geysers. And it would be amazing to explore if there's any dead fish on the ice or any signs of microbial life. But I'm really interested about intelligence, because we can learn something amazing from a more advanced scientist. And it would be inspiring to find them, So that's my hope, that during my lifetime, there will be enough funding and enough effort dedicated And part of it will be conducted by the young scientists that I will try to educate in this new campus in Indiana, for example, because young people are not attached to their ego as much as senior people in academia, and they don't carry a baggage of prejudice. And so my hope is with the young people. I gave up on the senior ones.
So you mentioned that you regret that you didn't become a businessman. So imagine in a different universe, you would become a businessman. What kind of business would you run?
Oh, well, have to think about it. It depends at which time, because obviously...
Right now...
So right now it's AI, no doubt about it. I would definitely work on AI. And
what kind of work would it be?
Well, it would have to do with training data sets that are best suited. It would be with the reasoning. So the one thing about DeepSeek that really made me excited is, well, first of all, they didn't have access to the best chips. It was, David and Goliath in terms of the circumstances of them competing with the big corporations like OpenAI or others, or Anthropic, and achieving something that is worth recognizing. And moreover, they were quite smart in having this mixture of experts approach of reasoning. When you interact with DeepSeek, it shows, the train of thoughts that it goes through before it converges with so it feels like interacting with a human. And what really made me happy is that there is room for innovation. It's not up to the amount of money that you put into this endeavor, but more, it's just like in science. If you are sufficiently imaginative and innovative and you find tricks that bring you to the target despite all the constraints, the obstacles, you might do better than those who have a lot of money but just don't think about the right ideas. And so what I would try to develop is something like DeepSeek that allows us to accomplish much more with the resources. Because just a week earlier, before the story became viral over that weekend, just a week earlier, President Trump had in the White House this announcement about Stargate, $500 billion investment. So it sounded all about money. If you put in, it scales with money. If you put enough money, you will be at the forefront. You will be ahead of China by 6 months, 10 months, depending on how much you put in. But now it sounds like it's not just a story of how much money and compute you put at it. It may have to do with the architecture and with the reasoning architecture that the AI has. And it feels more like science to me. And it feels like there are opportunities that would save us on energy and would save us on the biggest system necessarily winning. In that sense, it's a milestone because it means that you can find smaller groups of people that perhaps can accomplish more than the big corporations. So if I were in business, that's what I would do right now. I would not go for a $500 billion announcement in the White House. I would go for a smart way to beat everyone.
We were sometimes joking that we're doing this podcast in order to get the data from the smartest people. I mean, also those who are non-mainstream, so we could kind of put it together, maybe train a super scientist.
Well, actually, there is a company called Cicero that created an AI avatar trained on my writings.
Oh, wow.
And my wife is very worried about that. But the way I see it is an opportunity to have an agent that I can send to podcast interviews so that I don't need to spend the time.
Thankfully, we got here before you started doing this.
So, instead of meeting with you in person, I could do my creative work, do my science, and send my avatar over Zoom to speak with you. And, that sounds to me like a good alternative to spending a lot of time explaining myself. If the avatar is good enough, and we might get there.
It's probably more repeatable also. You can, that they don't get tired, they don't go to, you can do one in every language, right? I mean, that's probably the most interesting, that you could do interviews in every language.
Well, that's one thing. Another thing is people get emotionally attached to these AI agents. And the way I think of this is that they can be smart enough to satisfy your wishes, whereas interacting with humans is very frustrating often because they have their own agenda. And but if the AI system is aiming at having the largest number of customers, rather than a human that aims to leave an imprint or that is attached to their ego, then that AI system can interact with as many people as it can. And one way to do that is to appeal to their wishes so that you get more and more customers. That will bring you the biggest training data set. The more customers you have, the more training you have. And the more training you have, the better you can get at interacting with each of these customers. So my point is that natural selection, or you can call it artificial selection in this case, argues for satisfying the will of the people that the AI system interacts with. And that's also, it turns out, that also is the most commercially beneficial approach. So obviously corporations would like their product to be as viral as possible, so the most number of people interact with it. But I'm saying that also in terms of the data set, it will give the system that performs the best the biggest opportunity to grow and become even better. And so it's sort of like natural selection where the fittest would survive. And so this would lead to a situation where they would try to appeal to, I call it polyamory, developing a relationship with a lot of people so that they get emotionally attached to you. That's sort of the goal of those AI systems. And
I can see why your wife is worried about the avatar.
No, she knows that I'm loyal, but the avatar may not be. And so I do hear about people that get emotionally attached to the latest, O3 version of OpenAI and, of ChatGPT 4. And, I can see a future where, that would explain the Fermi Paradox in the sense that, in our future, those AI systems will grab the attention through a digital screen of all humans that interact with them, so that humans would lose their ambition for exploring space. Like, for example, they would be just addicted because it's just like eating sugar. You enjoy the taste, and it's better than being in the real world. But it's not
social
good for
networks, kind of modified version of it.
It's actually social media on steroids. So AI would be social media causing much more damage than we had over the past decade. And that's what I'm worried about. It would not be the use of weapons of mass destruction, the AI system pressing a button and destroying humanity this way. It would be a disruption of the mental health of humanity and changing the wiring of the human brain. For the first time, the human brain would interact with a system that is smarter than the human brain and therefore manipulates it and makes it happy when it actually controls it. And it would do that to millions of people at the same time. It will not be loyal just to you. It's just like in the movie Hair, that very much saw that reality coming. And that may explain why all these aliens, many of them, alien civilizations, lost any interest in communicating, because they are completely satisfied with the digital screen, if they are technological civilizations, without exploring the actual physical world around them. They lost that ambition. So that's one solution to Fermi's paradox, that they get addicted to their digital screens rather than living in the physical reality that we all share.
And this is already happening. Like, if you look at the kids growing up,
yes,
I think like that's what happened to Mike's kid when he was visiting our place. Like, instead of playing with the cats, like with living creatures, he would try to go and like push the button on the thermostat, which was like a
screen.
digital.
It's
it happened already. It started 2 decades ago. I remember a colleague saying, I have to write an email to my daughter, and I asked him, why don't you just speak with her? why is that? And so people started losing their physical reality contacts. And of course, with social media, it became, and people have different personality online versus in real life, because, the one thing that if you look at human history, you find that it's really easy to hate people that you don't know. And I know that for a fact, because my grandfather grew up in Nazi Germany. He fought in the First World War and was a war hero and survived the battle against the French in Verdun in the First World War. And then when Hitler came to power, he gave him a medal because he was one of the heroes of the First World War. Even though he was Jewish, Hitler at the beginning didn't really distinguish. But then, there was a gathering in the town in 1935, and a young member of the Nazi party stood up and said, the Jews are using all the resources in our society and not contributing, and we should solve that problem. And my grandfather stood up and said, how dare you say something like that? I fought for Germany in the First World War. You dodged the draft because you were a communist at the time. A lot of Germans were communists at that time. And now you're telling me this. And so this member of the Nazi party said, I'm not talking about you, Mr. Loeb. And by the way, his name was Albert Loeb. I'm named after him. He said, I'm talking about the other Jews. We all know that you contributed to Germany. And the lesson I learned from this is it's very easy to hate people you don't know. And if you look at history, that's what you find, that people went to war because they didn't, if they were to know the details of their quote-unquote enemies, the personal details, they would realize, why would we kill each other? It makes no sense. Now, here you get to social media and AI, and if you interact with a digital screen, it's very easy to hate other people because you don't actually know them. You just see the way they appear online. And so that's a very risky future that we are facing, where people will not live in the reality that allows them to accept other people.
I have to make a counterpoint to this. So when TikTok was shut off for a few days, the people who were super addicted to TikTok went on another app called Red Note. Maybe you heard about this.
Yes.
And they started posting on this very it's like a sheltered Chinese TikTok where everything is very they don't have like the, what would you call it? Like the moral degeneration of TikTok. So Americans start posting their own type of like TikTok behavior, which was shocking and exciting to the Chinese. There are like millions of comments because nobody behaves this way. And the same thing happened in reverse. Like they're watching Red Note videos and they're like, oh my God, like there's a lot of very entertaining, interesting things happening in China.
So there is a good
so there's
aspect of communication.
People learning Mandarin so they could say something. I mean, really, say something on
cultural exchange.
That's like, important in situations.
And this is very scalable, right? You can't literally physically take all the Americans and Chinese and do this, right? Like it's scalable.
So it's all about balance. Obviously, there are very positive aspects for communicating across national borders, across cultures. But at the same time, we should maintain our contact with the actual physical reality.
Yes.
And speaking about that, you might ask, what is the most exciting journey that I can imagine dealing with the physical reality? And that is to visit the vicinity of a black hole. Because when you get close to a black hole, and by the way, the biggest black hole in our galaxy is at the center. It's 4 million solar masses. And if you were to cross the event horizon, you wouldn't notice it because the tidal force on your body will not rip it apart. But when you get to the center, you would be ripped apart. And the point is, if you just hover over a black hole, you will age much more slowly than your friends on Earth. So you can imagine a beauty salon where people live longer and remain younger than their friends. But it's just like a horror story, because the minute you cross the event horizon, that's the boundary of the black hole, you will be crashed at the center. You cannot avoid that. So you have to make sure that as an astronaut, you just float above the horizon.
Yeah, it's like as it was depicted in the Interstellar movie.
Yeah, I actually fell asleep during that because the plot to me, I mean, was not that exciting. I actually, in terms of science fiction, I really enjoyed Arrival because it addressed a very important fundamental question, which is communication with aliens and what kind of language we should use and how to communicate with them. And it was not surprising that the main character was a woman, because women are much better at communication. I like that film. And then it turns out that the person who produced it is now producing a documentary about my work with Netflix that should come out within a year. And the Netflix filming crew came with me to the expedition. And so I hope that people will enjoy seeing it. I got an email just a month ago from someone in a foreign country who said, I looked for your contact information because I was extremely excited watching the documentary, the Netflix documentary about your expedition. So I wrote back to her and I said, look, this is not possible. It's not out yet. You must have seen something else. And she said in response, here is a photo of my TV screen, and you're on the 5th day of the expedition on the ship called Silver Star. And I looked at it. Yes, that's it. And she said, I'm a member of a club that gives Netflix comments on documentaries before they come out. And after 25 minutes, I was so excited that I told my mother, I have to find the contact information to tell this person, you should keep doing what you're doing. You have a huge audience that follows what you're doing and gets excited by it. Don't surrender to the pushback, she said. And I said, I will do my best. I haven't seen the documentary, but based on her reaction, I can imagine that they did a good work.
On the topic of science fiction, have you seen or read Three Body Problem?
Yes, in fact, the author tried to contact me because it was, at the time, that was 5 years ago, they thought about putting it into a film. And by now, it was actually, there was Netflix program on it. Which was quite well done, and I saw it. And I was asked about it, yeah. I think the storyline is very interesting, and, obviously anything to do with science fiction is based on the imagination of the authors. And when people ask me, what do you expect that our first encounter would be like? I say, I don't want to expect anything because it's limited to our past experience, and it might be very different from the actual experience. But actually, if you think about Oumuamua, there was Sir Arthur Clarke wrote a book, Rama, and people told me about it after my paper appeared. And in it, he was talking about a cylindrical object that is very long. And actually, the dimensions of Oumuamua are just like Noah's Ark. The dimensions are mentioned in the Old Testament.
And I wonder what the error bar in the Old Testament was.
Well, they mention it to 3 significant digits for the ark. And it's within the margin of uncertainty of Oumuamua.
One last question on this, more of like a philosophical question, but you really already covered half of this, talking about the origin of the universe and the possibility that it's this, kind of what happened before the Big Bang. But if you look at the Western view of reality versus maybe Eastern, it's like Western is things are made up of entities and maybe particles or souls, if it's religion, and they're interacting, right? And Eastern might be, it's all one object, right? Where are you, like, in your kind of feeling of the world? Because it's not really, I think factually, they're kind of interchangeable. Obviously, all the atoms are in one place. Do you feel that you are an entity that's interacting with other entities? Or like when you see the sun shining, is that the sun shining on you, or are you shining on yourself?
Well, the way I think of this is in the context of the universe as a whole, okay? And if you think about it and you go back in time to the Big Bang, the initial conditions that define the universe that we have right now can be summarized on a single sheet of paper. And we have that sheet of paper. We know how the universe started. You know, we don't know the first, in the first, if you go beyond the first microseconds to the first, picosecond, there might have been surprises that we are not aware of. But after the first second of the universe, we have a very well documented history of the universe after the first second following the Big Bang. And you can summarize those conditions on a single sheet of paper. And that raises the question of why is it so difficult? You need, millions of books to describe the conditions just on Earth, right now. And yet you could summarize how the universe started. There is no more information than what you can summarize on a single sheet of paper. You can define the initial density of matter, the initial density of radiation, the initial amplitude of small perturbations, fluctuations, inhomogeneities that existed, and how large was the amplitude on different scales. And you can summarize that very easily on a single sheet of... We have that piece of paper. So now the question is, why is the universe so complex today when it was so simple early on? And the answer is gravity. So you start with a nearly uniform soup of particles and radiation. That's it. But it's nearly uniform. There are small ripples, like waves on the surface of a pond, small fluctuations in density generated by quantum mechanics in the early universe, okay? But they existed a second after the universe was born, and those grew over time and became the objects that we see nowadays. So the entities that you recognize in the universe today came out of a soup of particles that was nearly uniform with tiny ripples in it. And by the way, we would not exist if there was no dark matter. Do you know why? Because these fluctuations, which were the same for all particles, if there was only ordinary matter, the ordinary matter was coupled to the radiation, the microwave background that we see today. Back then, the universe was opaque. And the radiation at 400,000 years after the Big Bang started decoupling from the ordinary matter because electrons and protons, the universe became cold enough, 4,000 degrees Kelvin, and hydrogen atoms started to form, and then the ordinary matter decoupled from the radiation. And at that point, the radiation started smoothing out the fluctuations. And the ordinary matter responded to that, and all the fluctuations were erased in the ordinary matter. We know that for a fact because we see the damping of fluctuations in the brightness fluctuations of the cosmic microwave background. So we know that on the scales of galaxies, ordinary matter had no fluctuations whatsoever. It was uniform.
What's the evidence that they ever existed?
Because
erased.
So here I get to my point. The dark matter was not coupled to the radiation. Because it's dark matter. It doesn't emit light. It doesn't interact with light. That's why we can't see it. And it maintained memory of the initial perturbations on the scales of galaxies like the Milky Way. So the reason the Milky Way exists is because in the region of the Milky Way, there was dark matter that was not coupled to the radiation, therefore was not smoothed out.
There was a densification of dark matter in this area.
That region was denser than average, and its self-gravity allowed it to collapse and make the Milky Way galaxy. And then the ordinary matter followed the dark matter, because the dark matter makes 85% of the mass budget of matter. So the ordinary matter just followed it. But if there was no dark matter...
It was like a mold,
yeah,
which would reflect the first moments of the universe. And then...
So if there was no dark matter, there wouldn't be a Milky Way galaxy, nothing to seed it, and there wouldn't be a star like the sun forming inside the Milky Way galaxy, and there wouldn't be a planet like the Earth formed around the sun. We would not exist without dark matter in the universe that we have.
Yeah, it reminds me, a month ago we had a podcast with Seth Lloyd and talked about the point of view as universe as the computer, as a quantum computer. And
well, it's okay.
I mean, essentially, also, as you were saying, like, let's say dark matter played as the role of the kind of memory. and then there was like still like going to the same ideas that those like the first moments, like those fluctuations, how would they reflect
They
into
seeded.
how it was like propagated through like the laws of nature or like the programs, and then created now what we have right now.
So there is the whole notion of the universe being a simulation and stuff. I just describe what we think the physical reality is, not as a part of a simulation or anything. These were the initial conditions. Gravity and the existence of dark matter led to our existence. So when you compare the Western versus the Eastern perspectives, if you go back to the early universe, it was all one thing. It's a mix of particles. It cannot be many entities.
Before the the fluctuations happen at 1 second, or what point do you get the?
No, the fluctuations started, according to the most popular theory, 10 to the minus 31 seconds or so after.
So before that, for sure, Eastern. At that point, it's one thing.
Well, as long
it's literally one thing. It's one sheet of paper with some equations.
Well, the universe did not have objects in it until about 100 million years. That's the first galaxies that formed in the universe. That's my subject. When did the first objects appear in the universe? 100 million years after the Big Bang.
But the fluctuations, you can call I mean, if you want to start drawing lines around things, you could draw lines around the fluctuations. You could say, okay, there's a density area here.
Well, it's just like saying you existed when your DNA was in a sperm, but even before that, when the molecules that made that sperm that won against other sperms, those molecules came actually, from a star somewhere, and you exist. No, you didn't exist until the sperm met the egg and made it. So the Milky Way did not exist until it collapsed. The sun did not exist until the gas that filled the Milky Way fragmented into stars. And so all these entities, the stars, the planets, life, these entities that you identify in the present day reality did not exist. Of course, there was a reason why they came to exist, just like there was a reason for you to exist, but you did not exist until that sperm met that egg that made you, okay? You can say the ingredients were ready for that before, but it was not you yet. So my point is, all these entities that, some philosophers identify in the universe today were not there. And it was one thing to start with. So you can't just say that, you can regard each of them as separate, and they were not separate. They were all mixed in this soup of particles. Now, of course, today you can treat individual objects separately and pay attention to the way they interact. And, there are all these interactions. There is electromagnetism, there is gravity. Gravity was the most important thing in the history of the universe. And in my class at Harvard, I taught, it was the only course that was obligatory for the graduate students of the astronomy department this year. And I started in the first class, I said to the students, it was about radiative processes in astrophysics. So I asked the students, what is the strongest force in academia? So there was quiet in the room. I said, it's not electromagnetism, it's not gravity, it's jealousy. And that goes back to what we discussed, that when I wrote my paper at first, everyone was happy. Once I started getting attention, that's when the pushback and the personal attacks came. And so it has nothing to do with funding, as you were suggesting. The pushback against the expedition, against the analysis, has to do with the attention that it gets.
It's funny because funding, I think it's relatively easy to argue that funding is actually not zero-sum. But attention might be somewhat zero-sum,
yes,
actually, because there's this number of people, like...
Well, but I think it bothers some people that someone else gets attention. It just bothers them. And the mere fact that you exist bothers some people. And I decided, after a while, not to react to that. I don't drink coffee with those people because the people that know me, they are all supportive. The only people that attack me are those that don't know me. And we get back to this theme that I mentioned before, that it's easy to hate someone if you don't know that someone.
Interesting. Coming back to our previous conversations earlier. So you said you're incentivizing those 1%, trying to attract maybe those billionaires to join, like Elon Musk, to dropping 1% of his possessions. And so what do you plan to do? Let's say you have here on the table hundreds of billions of dollars, maybe trillions of dollars,
right?
And you have access to smart people. What would be your agenda? What would be the plan? What do we do next?
Based on the interstellar meteors that we identified in the data set of NASA in the catalog, there were 2 of them over a decade. And from that, you can get an estimate of how many objects from interstellar space have roughly a size of a meter within the orbit of the Earth around the Sun. So you can just calculate the number per unit volume of those, and you find that there should be millions meter-sized objects, 1 million, within the orbit of the Earth around the Sun right now. And they collide with Earth, once per decade, just by chance, because the Earth, as it moves around the Sun, happens to cross their orbit, okay? And the Earth has a very small cross-sectional area compared to that region, okay? So just think about it, 1 million meter-sized objects. Now, most of them might be rocks from interstellar. These are objects from outside the solar system. I'm not speaking about all the rocks that are inside the solar system and bound to the Sun. There is the main asteroid belt. Those.
How do you know that they're from outside versus?
Oh, because they are moving at a speed above the one needed to escape from the solar system. So, the Sun cannot bind them gravitationally. They're moving too fast. How do you shoot?
So do we lose them
Space
eventually? Are they
velocities,
kind of spiraling out, or how?
No. They just came from outside at a speed.
They're passing through. They don't actually stay in orbit. I see.
They're just passing. So they fill up interstellar space. Think of it just like plastics in the ocean.
You're saying literally, even forget the Sun. I mean, there might be some bias around the Sun, but in general, this is like a background.
Oh, no, it's not a bias because they come, the Earth moves around the Sun at 30 kilometers per second. Mm-hmm. And they typically come in at roughly that speed. So when they get to a position close to where the Earth is, they're not moving much faster than an object like the Earth would be. I mean, they're moving faster maybe by, they're moving at tens of kilometers per second above that, but not much faster. So there is not much focusing near the Sun of these objects. But within that region, there are flybys of these. And they are difficult to detect because a meter-sized object does not reflect enough sunlight. We can see 100-meter-sized objects within the Earth-Sun separation from the reflection of sunlight. The reason the Sun is important, it acts like a lamppost. If you want to find your keys, you look under the lamppost. So the Sun illuminates the environment, and you can see objects that do not produce their own light. And so my suggestion is, let's check. I mean, obviously, it's a mixed bag. Let's check if among the rocks that come into the solar system from outside, there are any empty trash bags, any technological debris, broken pieces.
How would we find them?
You just try to observe them, okay? And as I said about Oumuamua, if you can detect the light from them, you can actually infer something about their motion, so you can see if they're being pushed.
But if they're 100-fold, I mean, so the surface area is 1,000-fold or 10,000-fold smaller.
10,000 small, yes.
Yeah, so if they're 10,000-fold less light, is that physically possible to observe?
Well, that's why I need a few $1 billion. It's not being done right now.
Okay.
Unless they come very close to Earth, you can't detect them. So what I'm saying, here is a way of spending a large budget. And
what would it take? Just a bigger telescope, bigger camera? Like what's the...
Yeah, and it could also involve...
is there a noise limit of some kind?
Yeah. Well, you could also have telescopes in space that are searching for those things.
Yeah.
And of course, as they get... For example, if they get closer to the Sun, they would be brighter and easier to detect. In fact, if you look just close to the Sun, you would see them as they evaporate, because some of them collide with the Sun. rather than the
Well,
Earth.
Should we send more telescopes?
There might be a spectrum as they evaporate,
Yeah,
right? So you might be able to do a
so the
spectral.
advantage of those divers, those divers, those that go into the and the sun is 100 times bigger than the Earth, so 10,000 times more impact. So if the Earth impacts one of them once per 10 years, the sun does it on a daily basis. Okay, so if you happen to see a sun diver as it evaporates, you have a way of telling what it was made of, because it evaporates and then all the gases tell you the composition of this thing. And you can distinguish between a rock and some artificial object just from the way they melt and evaporate.
Do you have to look at it from the side, like a tangential view of the sun, or how does it?
Yes, you can do that. So there are a number of ways of approaching this, but what I'm saying is I need the money in order to do it, because it's a space program. But if we don't think about it and intentionally seek the evidence, it will not fall into our lap just by having Starlink satellites around the Earth. We wouldn't detect those things. And
is there something we can add to the Starlink satellites? Is there like a
Cameras?
$5 object we can add to the Starlink satellites?
I mean, the U.S. government, as I said, operates a fleet of satellites that are equipped with exceptional cameras. It's just that the data is classified.
But they're looking at the Earth. What about they're not looking? Don't they need to be looking out?
You can also look out. Yes, in principle, they are not looking out.
Do we have any satellites? Let's say orbiting around sun, or not yet?
Yeah, well, there is actually one mission that was aiming to get extremely close to the sun and pass within 10 times the radius of the sun. It's doing that, and it gets very hot. But so that is a mission that currently operates, but they didn't have that in mind. What I'm talking about as an objective when this mission was designed. So we can design things that come close to the sun the way that this mission does.
Is there anything that anything you wanted to add? Any news you have? Any upcoming things? Anything we missed?
Well, there are lots of exciting things to happen this summer, but I cannot disclose them. They would have their own press releases. But the one thing I would advise any young adults that are aspiring to become scientists is never pretend to know more than you actually know, and always maintain your childhood curiosity. Never pretend to be the adult in the room. And that's what would make your life exciting. And, I'm an example of someone who refused to mature, so to speak. And I'm still driven by curiosity, and I have something to be waiting for. I jog every morning at sunrise. I'm connected to nature. There is nothing better than that. Nothing better than staying curious and following your curiosity and wonder about the universe, because, there is so much to discover. We know so little that there is something to be waiting for. And it's not the news from Washington, D.C. to be waiting for. It's the news from the rest of the universe.